As you lie here tonight, drifting towards sleep, you are moving through space at hundreds of miles per second, carried quietly by a vast galaxy spinning in the dark. Even in stillness, there is motion. Welcome. Get comfortable. Let your breathing slow. Tonight, we're going to drift through the cosmos together, exploring our home in the universe, the Milky Way galaxy. Before we begin our journey through the facts, I want you to remember something. Every atom in your body was forged in the heart of a star. You are, quite literally, made of stardust. The same elements that form distant suns flow through your veins. You are not separate from the cosmos. You are part of it. And tonight, as you close your eyes and let sleep find you, know that you belong to something vast, ancient, and beautiful beyond measure. The universe is not indifferent. It created you. And in creating you, it gave itself a way to know itself, to marvel at itself, to wonder. That alone is a kind of miracle. Now, let's begin. The Milky Way. Even the name sounds gentle, doesn't it? Milky. Soft. Like something you could drink before bed. The ancient Greeks saw it as spilled milk across the night sky. Other cultures saw a river, a path, a bridge between worlds. But what is it, really? Our galaxy stretches across space for 100,000 to 120,000 light-years. Imagine that for a moment. Light, traveling at 186,000 miles per second, would take 100,000 years to cross from one edge to the other. It's almost impossible to grasp, and that's okay. Let the number wash over you. 100,000 years of light, streaming through the darkness. And here's something remarkable. The Milky Way isn't flat. You might picture galaxies as perfect disks, spinning elegantly like plates. But our galaxy is warped. It bends and ripples like a record left too long in the sun. This warping comes from the gravitational tugs of smaller galaxies that orbit us, pulling at our edges, distorting our shape. We are not isolated. Even galaxies have neighbors, and those neighbors leave their mark on us. Within this warped disk, between 100 billion and 400 billion stars shine. Think about that. 400 billion. If you counted one star every second, it would take you nearly 13,000 years to count them all. And you, lying here tonight, are connected to every single one of them through the ancient laws of gravity and light. 400 billion suns, each potentially with planets, each with its own story written in fire and time. Some of those stars have already died, their light still traveling toward us like messages from ghosts. Others are being born right now, this very moment, condensing from clouds of gas in stellar nurseries scattered throughout the spiral arms. The Milky Way is considered medium-sized, which is humbling in its own way. We're not the largest galaxy in the universe. We're not the smallest. We're somewhere in the middle, ordinary and extraordinary all at once. It's a bit like Earth itself, isn't it? Not the biggest planet. Not the smallest. Just right for life. Just right for you. Now here's where it gets strange, in that beautiful way that the universe so often does. 90% of the Milky Way's mass is invisible. It's not stars. It's not planets. It's not dust or gas or anything we can see or touch. It's dark matter. Dark matter doesn't emit light. It doesn't absorb light. It doesn't interact with light at all, as far as we can tell. We only know it's there because of its gravity, the way it pulls on things we can see. It forms a vast halo around our galaxy, cradling it, holding it together. Without dark matter, the Milky Way would fly apart. The stars would drift away into the void. So even though we can't see it, can't touch it, can't even really understand what it is, it's holding us, keeping us together. There's something oddly comforting about that, isn't there? An invisible force, keeping everything from falling apart. The Milky Way is what astronomers call a barred spiral galaxy. At its center lies not just a bulge of stars, but a bar. A straight structure made of stars and gas, stretching across the galactic core like the handle of a cosmic whisk. From the ends of this bar, spiral arms unfurl into space. We have at least 4 major arms. Their names are lovely: the Perseus arm, the Norma arm, the Scutum Centaurus arm, and the Sagittarius arm. Some astronomers argue there are more, smaller arms between these major ones. The structure is still being mapped, still being understood. Even our own home galaxy holds mysteries. These arms aren't solid. They're more like traffic jams of stars and gas, regions where matter bunches up as it orbits the galactic center. Stars drift in and out of the arms over millions of years, like cars merging in and out of slow lanes on a cosmic highway. We live in one of these arms, in a smaller spur called the Orion Spur, nestled between the larger Perseus and Sagittarius arms. From our vantage point on Earth, we see the Milky Way as a band of light across the night sky. We're looking at it edge-on, from inside, like trying to see the shape of a forest when you're standing among the trees. For thousands of years, humans looked up and wondered what that cloudy band of light could be. Only in the early 1600s, when Galileo turned his telescope skyward, did we realize it's stars. Countless stars, too far away and too close together for our eyes to separate them. And now we know so much more. We know our place in it. We know its size, its shape, its motion. We know it's moving through space, carrying us with it. We know it will one day collide with our nearest large neighbor, the Andromeda Galaxy, though not for another 4 billion years or so. You can rest easy tonight. That collision is a very, very long time away. The Milky Way is ancient. Most of its stars are billions of years old. But it's also alive, constantly making new stars, constantly changing, constantly evolving. It's both a monument to the deep past and an engine of the future. And you're part of it. Every breath you take, every thought drifting through your mind as sleep approaches, happens here, in this galaxy, in this particular moment in its 14 billion year story. You are here. You are home. And the Milky Way, vast and warped and mysterious, spins silently through the dark, carrying you with it. Rest now. Let the numbers and the distances fade. Let yourself float among those 400 billion stars. You belong here, in this cosmic river, in this band of light. Let's travel back. Way back. To the beginning. Close your eyes and imagine nothing. True nothing. No stars, no planets, no light. Just potential, coiled up in a single point, smaller than an atom, containing everything that would ever be. 13.8 billion years ago, that point exploded. The Big Bang. Space itself began to expand, carrying matter and energy outward in all directions. The universe was born. And just 200 million years later, in cosmic terms barely a heartbeat, our galaxy began to form. 13.6 billion years ago. Try to hold that number gently in your mind. 13.6 billion. The Milky Way is almost as old as the universe itself. When our galaxy first took shape, the cosmos was still young, still hot, still finding its form. In those early moments, there were no stars yet. Just vast clouds of hydrogen and helium, the simplest elements, floating in the darkness. But gravity was already at work, patient and relentless. It pulled at these clouds, drawing them together, condensing them. Slowly, over millions of years, the gas began to clump. It began to spin. And as it spun, it flattened into a disk, the way pizza dough flattens when you spin it in the air. The laws of physics are simple, elegant. Spinning things flatten. And so our galaxy found its shape. The first stars ignited. Massive, brilliant, short-lived. They burned through their fuel in just a few million years and exploded as supernovae, seeding the cosmos with heavier elements. Carbon, oxygen, iron. The building blocks of planets. the building blocks of life. Of you. These ancient stars are mostly gone now, their light long faded. But their legacy remains in every atom of every element heavier than helium in your body. The Milky Way didn't snap into existence all at once. It grew slowly, patiently. The disk and the central bulge, the main structures we recognize today, took shape between 10 and 12 billion years ago. That's a construction project that lasted billions of years. No rush. The universe has time. Picture it. Clouds of gas swirling inward, stars forming in clusters, everything slowly organizing into the barred spiral structure we know today. The center grew dense with stars, packed so tightly that if you lived on a planet there, your night sky would be ablaze with thousands of stars brighter than Venus appears to us. No true darkness, just eternal twilight. But the Milky Way didn't build itself alone. It had help, though perhaps help isn't quite the right word. Our galaxy is a cannibal. Throughout its history, the Milky Way has consumed smaller galaxies. These dwarf galaxies, wandering too close, were caught by our gravity and torn apart. Their stars were absorbed into our structure. Their gas was fed into our star-forming regions. They became part of us. One of the most recent meals was the Canis Major dwarf galaxy. It's still being digested, its stars streaming through our outer regions, slowly mixing with our own. When you look up at certain parts of the night sky, some of the stars you see might have once belonged to another galaxy entirely. Immigrants, refugees, now citizens of the Milky Way. This process of galactic cannibalism is ongoing. Right now, we're pulling apart the Sagittarius dwarf elliptical galaxy, our nearest neighbor. Over the next few billion years, it will disappear completely, its stars scattered throughout the Milky Way like salt dissolved in water. It sounds violent, doesn't it? But it happens so slowly, so gently. Stars almost never collide. Space is so vast, so empty, that even when two galaxies merge, the stars simply pass by each other like ghosts. It's a collision in slow motion, played out over hundreds of millions of years. This is how galaxies grow, not by forming all their stars at once, but by gathering them over time, by merging and mixing, by becoming something new while carrying the memory of everything they once were. The Milky Way has layers, like a tree. And like a tree, these layers tell us its history. The thin disk, where we live, contains younger stars. When I say younger, I mean they average between 5 and 7 billion years old. Still ancient by human standards. Our Sun is about 4.6 billion years old, relatively young compared to many of its neighbors. These thin disk stars orbit in neat, circular paths around the galactic center. They're the current generation, enriched with heavy elements from all the stars that came before. But beneath the thin disk lies the thick disk. These stars are older, much older, more than 10 billion years old. They formed when the galaxy was younger, when there were fewer heavy elements around. Their orbits are more chaotic, more elliptical. They bob up and down through the galactic plane like horses on a carousel. They remember a wilder time, when the Milky Way was still settling into its current form. And surrounding everything is the halo, a spherical cloud of the oldest stars of all. These are the first generation, the pioneers, formed from the primordial gas of the early universe. They're metal poor, as astronomers say, meaning they contain very few elements heavier than hydrogen and helium. They're survivors from the beginning, witnesses to nearly the entire history of the galaxy. When you look at the Milky Way, you're seeing not just space, but time. The layers of stars are layers of history, each generation built on the remains of the last. There's something beautiful about that. The idea that nothing is ever truly lost. That every star that ever lived contributed something to what came after. That we are built from the dust of ancient suns, and one day, when our sun dies, its atoms will be recycled into new stars, new worlds, maybe new life. The circle continues. The galaxy remembers. 13.6 billion years. From scattered clouds of gas to this magnificent spiral, home to hundreds of billions of stars and at least one planet where a person lies down at night and wonders about it all. The Milky Way is old, but not static. It's still growing, still changing, still writing its story. And your story, brief as it is on cosmic timescales, is part of that larger story. You are the galaxy knowing itself. You are its consciousness, its poetry, its moment of self-reflection. The ancient stars in the halo have been shining since before Earth existed. They've watched our solar system form, watched life emerge, watched everything you've ever known come into being. And they're still there, patient and eternal, watching still. Rest now in the embrace of deep time. Let billions of years wash over you like a warm wave. You are young, so young, and that's a gift. But you're also ancient, made of elements forged in the very beginning, in the hearts of stars that died before the Earth was born. You are both new and old, temporary and eternal. The Milky Way remembers everything. And for this moment, you are part of what it remembers. Let's drift toward the heart now. The center of everything we've been talking about. The core of the Milky Way. Every galaxy has a center, a point around which everything else revolves. And at our center, hidden behind thick clouds of dust and gas that block visible light, something extraordinary waits in the darkness. A supermassive black hole. Its name is Sagittarius A*, pronounced Sagittarius A star. Astronomers call it SGR A* for short. It sits precisely at the galactic center, 26,000 light-years from Earth, in the direction of the constellation Sagittarius. For a long time, we suspected it was there. We could see stars near the galactic center moving in strange ways, whipping around something we couldn't see at tremendous speeds. Like watching leaves caught in a whirlpool, we knew something powerful had to be pulling them, but we couldn't see it directly. Then, in 2022, astronomers released the first image of Sagittarius A star. Not the black hole itself, because black holes are, by definition, black. They don't emit light. But they're surrounded by hot gas and dust that glows as it spirals inward, creating a ring of light around the darkness. And that ring, that beautiful golden ring of doomed matter, we can photograph. Sagittarius A* has a mass equal to about 4.1 million of our suns. Let that settle in your mind for a moment. 4 million suns, compressed into a space so small, so dense, that not even light can escape its gravity. The black hole itself, the event horizon where the point of no return exists, has a diameter of about 14 million miles. That sounds large, and it is. You could fit several suns side by side across that distance. But compared to the black hole's mass, it's incredibly small. All that matter, compressed into a region smaller than Mercury's orbit around the Sun. Imagine standing at a safe distance, watching. You'd see stars orbiting this invisible point at speeds of thousands of miles per second. One star, called S2, completes an orbit around Sagittarius A* in just 16 years. Its orbit brings it so close to the black hole that it experiences Einstein's relativity in measurable ways. Time moves slightly slower for it. Space warps around it. But don't worry. We're far away. 26,000 light-years away. The black hole's gravity is strong at the center, but here, where we are, it's negligible. It holds the galaxy together through its gravity, yes, but gently. We orbit it once every 250 million years or so, a stately, peaceful revolution. Sagittarius A* is, remarkably, quite quiet right now. It's not actively feeding much. Most supermassive black holes at the centers of galaxies are either sleeping or feasting, and ours is mostly sleeping. Occasionally it snacks on a stray cloud of gas or an unlucky star that wanders too close, and when it does, it flares brightly in X-rays and radio waves. But most of the time, it's calm. This is good for us. Active black holes, the ones that are constantly feeding, blast out jets of energy and radiation that would sterilize any nearby solar systems. We're fortunate to live around a quiet giant. But Sagittarius A** wasn't always this peaceful. Above and below the galactic center, extending for 25,000 light-years in each direction, are two enormous structures called the Fermi bubbles. 25,000 light-years. That's nearly half the distance from the galactic center to the edge. These bubbles are vast beyond imagining, each one large enough to contain thousands of smaller galaxies. They glow in gamma rays, the highest energy form of light, invisible to our eyes but visible to space telescopes like the Fermi Gamma Ray Space Telescope, which discovered them in 2010. From our perspective inside the galaxy, they're hard to see, like trying to notice the walls of a room when you're standing inside it. But from outside, from another galaxy looking at us, the Fermi bubbles would be one of the most prominent features of the Milky Way. How did they form? The answer, we believe, lies in the past behavior of Sagittarius A*. Millions of years ago, perhaps 6 to 9 million years in the past, our central black hole wasn't sleeping. It was feasting. Maybe it captured and devoured a massive gas cloud. Maybe several stars fell in at once. Whatever happened, Sagittarius A** roared to life. As matter spiraled into the black hole, not all of it made it past the event horizon. Some of it was funneled along magnetic field lines and shot outward in powerful jets, perpendicular to the disk of the galaxy. These jets carried tremendous energy, plowing through the gas above and below the galactic plane. The collision between these jets and the surrounding gas created shockwaves, heating everything to millions of degrees, creating the glowing bubbles we see today. It was an outburst, a tantrum, a moment when the quiet giant at our center reminded the galaxy of its power. And then, it went quiet again. The feast ended. The jets shut off. But the bubbles remain, slowly expanding, slowly fading, like echoes of ancient thunder. In another few million years, they'll dissipate completely, their energy finally spent. But for now, they stand as monuments to the violence our galaxy is capable of, even if it's currently at peace. There's something almost reassuring about knowing that even the Milky Way has a past, has moments of chaos and calm. It's not static. It's lived through dramatic events. And it survived them all. The core of the galaxy is a place of extremes. Temperatures reach millions of degrees. Stars are packed so densely that collisions, rare elsewhere, occasionally happen. Time runs differently there, warped by the intense gravity. It's a realm where the normal rules break down, where Einstein's equations replace Newton's, where reality becomes strange. But it's also the anchor, the center around which we all revolve. Without that supermassive black hole, the galaxy would be different, less stable, less organized. The black hole's gravity helped shape the Milky Way, helped form the spiral arms, helped turn scattered clouds of gas into the elegant structure we inhabit. It's the heart of the galaxy. Not in the romantic sense, not pumping blood, but in the structural sense. The thing around which everything else is built. And it's quiet tonight. Sleeping. Dreaming, perhaps, whatever dreams a black hole might have. 4 million suns, compressed into darkness. Surrounded by a golden ring of light. Orbited by stars moving faster than we can comprehend. Sitting beneath vast gamma-ray bubbles that stretch halfway across the galaxy. The center holds. And it's been holding for 13 billion years. You're safe here, far out in the spiral arms. The core's power is distant, contained, no threat to you or Earth or anything you love. It's simply there, doing what it's done since the galaxy was young, anchoring everything, giving structure to the spiral. In a way, we're all orbiting that center. Not just our solar system, but everything. Every star you've ever seen. Every planet. Every comet an asteroid and cloud of dust. All of us, moving together in a slow dance around the dark heart of the Milky Way. It takes us 250 million years to complete one orbit. The last time we were at this exact spot in our galactic orbit, dinosaurs didn't exist yet. The next time we come around, who knows what will exist? What species? What civilizations? What wonders? The galaxy turns. The center holds. And life, precious and improbable, flourishes in the safer regions far from the core's intensity. Rest now. Let the image of that golden ring fade from your mind. Let the vast gamma-ray bubbles dissolve into peaceful darkness. The core is there, but you don't need to think about it. It will do its job without your attention. Everything revolves. Everything finds its orbit. Including you, here, now, finding your way towards sleep. The center is quiet tonight. And so can you be. Breathe slowly. The galaxy breathes with you, expanding and contracting in its own vast rhythms. You are far from the center, and that is good. You are in the safe zone, the habitable zone, where stars live long and planets can form and life can wonder at it all. Now let's come home. Let's find ourselves in this vast spiral. You might think, living here, being part of it, that we'd have a clear sense of where we are. But for most of human history, we didn't. We couldn't see the forest for the trees. We were like someone trying to draw a map of an entire city while standing on a single street corner, unable to move, unable to gain perspective. Only in the last century did we really figure it out. Where we are. What our address is in the galaxy. Earth lies 26,000 to 28,000 light-years from the galactic center. The measurements vary slightly depending on the method used, but let's settle on about 27,000 light-years. We're roughly halfway out, in the suburbs of the galaxy, far from the crowded downtown core but not quite in the rural outskirts either. It's a comfortable distance. Close enough that we're firmly part of the main galactic disk, far enough that we're safe from the chaos and radiation near the center. It's what astronomers call the galactic habitable zone, the region where solar systems like ours can exist peacefully for billions of years without being disrupted. Our sun doesn't sit in one of the major spiral arms. It's between them, in a smaller structure called the Orion Spur, sometimes called the Orion Arm. Think of it as a branch connecting two larger limbs. It's about 10,000 light-years long and 3,500 light-years wide, and it's home to some of the most familiar sights in our night sky. The bright stars of Orion's belt, the brilliant blue supergiants of the Pleiades, the red glow of the Betelgeuse, all our local neighbors are part of this spur. We're in good company, surrounded by stellar nurseries where new stars are being born even now. The Orion Spur sits between the Perseus Arm, which lies farther from the galactic center than we do, and the Sagittarius Arm, which lies closer in. If you could see the galaxy from above, our little spur would look like a short segment connecting these two major arms, like a spoke between the curves of a spiral. We're not in the main flow of traffic, which is another stroke of luck. The major spiral arms are where density waves compress gas and trigger intense star formation. That means lots of massive stars, which means lots of supernovae. Living in a major arm would be more exciting, certainly, with new stars blazing to life all around us, but it would also be more dangerous. Radiation from nearby supernovae could damage planetary atmospheres, including our own. Here in the Orion Spur, things are calmer. Stars form at a more leisurely pace. The neighborhood is stable, settled, safe enough for complex life to evolve over billions of years without being sterilized by cosmic catastrophes. But safe doesn't mean still. We're not sitting in one place. The Sun, along with Earth and all the planets, all the asteroids and comets, everything in our solar system, is orbiting the galactic center. We're moving at about 550,000 miles per hour, or roughly 230 kilometers per second, in our orbit around the distant black hole at the galaxy's heart. At that speed, It takes us approximately 240 million years to complete one full orbit. Astronomers call this a galactic year, or sometimes a cosmic year. Think about what that means. The last time Earth was at this exact position in the galaxy, it was the Triassic period. Dinosaurs were just emerging. Mammals didn't exist yet. Pangaea was just beginning to break apart. Everything we think of as the age of dinosaurs, all 65 million years of it, happened in just over a quarter of one galactic orbit. Humans, modern humans, have existed for maybe 300,000 years. We've completed only about 1/800th of a single trip around the galaxy. We're newcomers. We're barely getting started. And yet, in that tiny fraction of one orbit, we've figured out where we are. We've mapped the galaxy from the inside. We've located the center, measured our distance from it, tracked our motion through space. That's remarkable when you think about it. But our motion doesn't stop there. The Sun isn't just orbiting the galactic center in a simple circle. It also bobs up and down, oscillating above and below the galactic plane as it goes. Right now, we're slightly above the plane, moving upward. In about 10 to 15 million years, we'll reach the peak of our oscillation, about 300 light-years above the mid-plane, and then we'll start falling back down. This bobbing motion takes about 60 to 70 million years to complete one full cycle. Some scientists have speculated that our passages through the denser parts of the galactic plane might trigger comet showers from the Oort cloud, potentially causing periodic mass extinctions on Earth. It's controversial, and the evidence is debated, but it's a reminder that our position in the galaxy might matter more than we realize. And there's another motion, larger still. The entire Milky Way is moving through space. We're not floating in some fixed cosmic reference frame. We're traveling at about 600 kilometers per second, nearly 1.3 million miles per hour, through the universe. Where are we going? We're moving as part of the local group, a small collection of galaxies bound together by gravity. The local group includes the Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and about 50 smaller dwarf galaxies. We're all moving together, orbiting each other in a slow, complex dance. And the local group itself is moving, pulled by the gravity of even larger structures. We're falling, very slowly, toward the Virgo supercluster, a massive collection of galaxy clusters about 65 million light-years away. And the Virgo supercluster is itself being pulled toward an even larger structure called the Shapley supercluster. It's motion within motion within motion. The Earth spins. The Earth orbits the Sun. The Sun orbits the galactic center. The galaxy moves through the local group. The local group moves through the universe. Everything is in motion, falling through space and time, and yet, to us, sitting here, everything feels perfectly still. You can't feel any of it, can you? Not the Earth's spin, not its orbit, not the Sun's motion through the galaxy. It all happens so smoothly, so constantly, that we've come to take stillness for granted. But we're moving. Always moving. You, right now, as you lie there breathing slowly, are traveling through space at over a million miles per hour when you add up all the different motions. And yet, you're also standing still. Because motion is relative. Relative to the Earth, you're not moving at all. Relative to the Sun, you're orbiting at 67,000 miles per hour. Relative to the galactic center, faster still. Relative to the cosmic microwave background, the closest thing we have to an absolute reference frame, fastest of all. Which perspective is true? All of them? None of them? It depends on where you're standing, what you're measuring against. This is our place. 27,000 light-years from the center. In a spur between two spiral arms. Orbiting peacefully, bobbing gently, moving through space at tremendous speeds that feel like perfect calm. We are neither at the center nor at the edge. We are not in the most active regions nor in the most desolate. We are in between, in the middle, in the Goldilocks zone of the galaxy where everything is just right. And from here, from this particular place, at this particular moment in cosmic history, life emerged. Consciousness arose. You came to be. Your address is specific: planet Earth, solar system, Orion Spur, Milky Way galaxy, local group, Virgo supercluster, observable universe. You are here. You have always been here, because here is wherever you are. The galaxy carries you. The sun warms you. The earth holds you. And tonight, as you drift towards sleep, all of that continues. The galaxy doesn't stop turning because you close your eyes. The sun doesn't stop shining because you rest. Everything keeps moving, keeps spinning, keeps falling through space. You are part of the motion. You are part of the dance. 240 million years from now, if anything of humanity remains, we'll have completed another full orbit. We'll be back at this spot, looking out at perhaps a very different universe, with different stars in our night sky, different neighbors in our cosmic community. But for now, for tonight, we are here. In this moment. In this place. 27,000 light years from the center of everything. It's a good place to be. Safe. Stable. Beautiful. Rest now, traveler. You're exactly where you need to be. The galaxy knows where it's going, even if we don't. Trust the motion. Trust the orbit. You are home. You have always been home. And the Milky Way carries you gently through the dark, as it has for 4.5 billion years, as it will for billions more. Sleep, child of the Orion Spur. Your place in the cosmos is secure. The galaxy holds you. And you are exactly where you belong. Every living thing has a structure, a skeleton, a framework that gives it shape, that holds everything together. The Milky Way is no different. It has bones, if you will. Architecture. A beautiful, intricate design that took billions of years to build. Let's explore that structure now. Let's see how our galaxy is put together. At the very heart, we've already visited the supermassive black hole. But surrounding it, extending outward from the core, is the central bar. This bar is made of stars, billions of them, moving in elongated orbits that create a rectangular structure through the galactic center. It's about 27,000 light-years long, roughly the same distance as we are from the center. If you could see the galaxy from above, this bar would be one of the most prominent features, a bright spine of stars cutting through the nucleus. Bars like this are common in spiral galaxies. About 2/3 of all spirals have them. For a long time, we weren't sure if the Milky Way had one because, again, we're inside it, trying to see the shape from within. But careful measurements of star positions and velocities confirmed it. We live in a barred spiral, and that bar plays a crucial role in the galaxy's life. The bar acts like a cosmic conveyor belt, funneling gas from the outer regions toward the center. This gas feeds star formation in the inner galaxy and, occasionally, feeds the central black hole. The bar also influences the spiral arms, helping to maintain their shape and structure. It's not just decoration. It's functional, essential to how the galaxy operates. From the ends of this bar, the spiral arms unfurl. These arms have names that sound like they belong in fantasy novels. The Perseus arm, the Scutum Centaurus arm, the Norma arm, the Sagittarius arm, each one curving gracefully outward from the center, each one traced by the light of young, hot stars. The Perseus arm lies on the outer edge of where we are. It's named after the constellation Perseus, which lies in that direction from our perspective. It's rich with star-forming regions, nebulae glowing pink and red with ionized hydrogen, stellar nurseries where new suns are being born. The Scutum Centaurus arm is one of the two major arms, along with Perseus. It contains some of the galaxy's most active star-forming regions. If you could see the Milky Way from outside, This arm would blaze brightly with the blue-white light of massive young stars. Between these major arms lie smaller structures, spurs and branches, including our own Orion spur. The exact number of arms is still debated. 2 major arms. 4 more. The structure is complex, and dust obscures our view of much of the galaxy. We're still mapping our own home, still discovering its intricacies. These spiral arms aren't rigid structures. Stars don't stay in them permanently. Instead, the arms are density waves, regions where stars and gas bunch up temporarily as they orbit the galactic center. Think of traffic on a highway slowing down and bunching up, then spreading out again. The cars move through the traffic jam, but the jam itself stays in roughly the same place. That's what spiral arms are. Cosmic traffic jams. And where the gas bunches up, where it gets compressed by the density wave, something magical happens. Star formation. The compressed gas collapses under its own gravity, fragmenting into clumps that ignite as new stars. This is why the spiral arms glow so brightly. They're lit up by these newborns, massive stars that burn hot and blue and die young. Our Sun formed in or near a spiral arm 4.6 billion years ago. Since then, we've drifted out into the quieter space between arms, into the Orion spur. We've been wandering, moving through the galactic disk on our own trajectory, sometimes passing through arms, sometimes between them. The spiral structure is beautiful, but it's also dynamic, always changing, always evolving. New stars form. Old stars drift. The arms shift and reshape over millions of years. Now, imagine looking at the galaxy edge-on, from the side. You'd expect to see a flat disk, perfectly horizontal, like a plate. But that's not quite what you'd see. The galactic disk is warped. It bends. It twists into an S shape, with one side curving upward and the other downward. Near the center, the disk is flat, but as you move outward, past about 40,000 light-years from the core, it starts to warp noticeably. Why? Because of gravitational interactions with our satellite galaxies, the small galaxies that orbit the Milky Way. The large and small Magellanic Clouds, our 2 most prominent companions, tug at our outer regions with their gravity. Over time, this tugging has distorted the disk's shape. It's a reminder that the Milky Way doesn't exist in isolation. It has neighbors. It has relationships. And those relationships leave marks, change its shape, influence its structure. The warp is subtle from our perspective inside the disk. We don't notice it in our daily lives, obviously. But when astronomers map the positions of stars and gas clouds in the outer disk, the warp becomes clear. The galaxy is bent, twisted, imperfect. And that imperfection is beautiful. It shows that the Milky Way is a living, dynamic system, responding to its environment, shaped by forces beyond itself. Beyond the visible disk, beyond the spiral arms and the warped edges, lies the halo. The halo is a roughly spherical region that surrounds the entire galaxy. It contains some of the oldest stars in the Milky Way, ancient red giants born in the first billion years after the Big Bang. These stars are metal poor, formed when the universe contained almost nothing but hydrogen and helium. They are witnesses to the galaxy's youth. The halo also contains globular clusters, dense spherical collections of hundreds of thousands of stars, each cluster like a small city orbiting through the emptier spaces above and below the galactic plane. There are about 150 known globular clusters associated with the Milky Way, each one billions of years old, each one a relic of ancient times. But most of the halo isn't made of stars at all. It's made of dark matter. Remember the invisible substance that makes up 90% of the galaxy's mass? It's concentrated in the halo, forming a vast sphere that extends outward for nearly 1 million light-years. 1 million. 10 times the diameter of the visible disk. This dark matter halo is essential. Its gravity holds the galaxy together. Without it, the outer stars would be moving too fast to stay bound. They'd fly off into intergalactic space, and the Milky Way would slowly dissolve. So even though we can't see it, can't touch it, can't even directly detect it, the dark matter halo is perhaps the most important structural element of the galaxy. It's the invisible skeleton, the framework upon which everything else is built. 1 million light-years. That means the Milky Way is far larger than the bright disk we see in pictures. Most of the galaxy is invisible, dark, empty space punctuated by occasional ancient stars and mysterious dark matter. It's humbling, isn't it? To realize that what we see is just a small fraction of what's really there. The visible galaxy is like the tip of an iceberg, with the vast bulk hidden beneath the surface. The structure of the Milky Way is elegant. A central bar feeding gas inward. Spiral arms where that gas becomes stars. A warped disk responding to external influences. A halo of ancient stars and invisible matter extending outward into the darkness. Each piece serves a purpose. Each piece fits together with the others. It's a machine, in a way, but a machine that builds itself, maintains itself, evolves itself over billions of years. And we live inside this machine. We're part of its structure. Every atom in your body passed through several generations of stars in the galactic disk before ending up in you. You're made from recycled galaxy. You're built from the same stuff as the spiral arms, just arranged differently, just temporarily organized into the pattern that is you. The galaxy is not something separate from you. You are not an observer standing outside looking in. You are part of the structure. A tiny part, yes, but a part nonetheless. The Milky Way skeleton supports you just as your skeleton supports you. The framework is there, invisible mostly, unnoticed, but essential. 27,000 light-years of central bar. Spiral arms stretching across 100,000 light-years of disk. Warped edges responding to the pull of companion galaxies. A halo extending 1 million light-years into space, holding everything together with invisible gravity. This is the architecture of home. This is the framework within which your entire existence unfolds. And tonight, as you rest, that structure remains. The bar continues funneling gas. The spiral arms continue forming stars. The disk continues its slow warp. The halo continues holding everything in its patient, invisible embrace. The skeleton of the galaxy is strong. It's been standing for 13 billion years. It will stand for billions more. You can rest against it. You can trust it. The structure holds. And within that structure, you are safe, you are home, you are exactly where the universe intended you to be. The Milky Way isn't empty, space decorated with stars. It's full, brimming, actually, with material, with substance, with the raw ingredients of creation. When we look up at the night sky, we see stars, points of light. But between those points lies something equally important, even if it's mostly invisible to our eyes. Gas, dust, the stuff between the stars. About 10 to 15% of all the visible matter in the galaxy exists in this form. Not locked up in stars or planets, but drifting freely through space. Clouds of hydrogen and helium, laced with heavier elements. Tiny grains of dust, each one smaller than a particle of smoke, made of carbon, silicon, iron, compounds that formed in the atmospheres of dying stars. This interstellar medium, as astronomers call it, is where new stars are born. It's the womb of the galaxy. In some regions, this gas is thin, spread out, nearly invisible. Just a few atoms per cubic centimeter. Less dense than the best vacuum we can create on Earth. This is the warm interstellar medium, heated by starlight and supernova shockwaves to thousands of degrees. In other regions, the gas is much denser. It clumps together, cools down, forms clouds. These molecular clouds, as they're called, are cold and dark, just 10 to 20 degrees above absolute zero. They're the densest places in the interstellar medium, with thousands or even millions of atoms per cubic centimeter. Still incredibly empty by Earth standards. The air you're breathing right now contains about 10 billion molecules per cubic centimeter. Even the densest molecular cloud is emptier than the best vacuum chamber on Earth. But by cosmic standards, they're dense enough. Dense enough for gravity to take hold. And when gravity takes hold of a molecular cloud, stars are born. Some of these clouds glow, not with their own light, but with borrowed light from nearby stars. When a massive, hot star forms inside or near a cloud of gas, its ultraviolet radiation ionizes the surrounding hydrogen, stripping electrons from atoms, creating a plasma that glows with a characteristic reddish-pink color. These are emission nebulae, and they're among the most beautiful objects in the galaxy. The Orion Nebula is the most famous example. Visible to the naked eye as a fuzzy patch in Orion's sword, it's a stellar nursery just 1,500 light-years away. Inside that glowing cloud, hundreds of new stars are forming right now, even as you lie here. Infant suns, still wrapped in their birth cocoons of gas and dust, heating up, beginning to shine. If you could see the Orion Nebula up close, it would take your breath away. Vast curtains of glowing gas, sculpted by stellar winds into impossible shapes. Towers and pillars and waves, all glowing in shades of red and pink and purple. And scattered throughout, the fierce blue-white points of newborn stars, burning with the intensity of youth. These nurseries exist throughout the galaxy. Wherever there are molecular clouds and massive stars, there are emission nebulae. The Eagle Nebula, with its famous pillars of creation. The Carina Nebula, home to some of the most massive stars known. The Lagoon Nebula, the Trifid Nebula, dozens more, each one a factory of stars. But most molecular clouds don't glow. Most are dark, cold, invisible except as shadows against the background stars. These dark nebulae are equally important. They're the reservoirs from which future generations of stars will form. The galaxy is constantly recycling this material. Nothing is wasted. Nothing is truly lost. Right now, the Milky Way is forming stars at a rate of about 1 to 2 solar masses per year. That means every year, enough gas condenses and ignites to create 1 or 2 stars the size of our Sun, or one massive star, or dozens of smaller stars. The exact mix varies, but the total rate is roughly constant. 1 to 2 stars per year might not sound like much. But remember, this has been going on for billions of years. 1 star per year for 10 billion years is 10 billion stars. That's how the galaxy built its stellar population. And the process continues. As you sleep tonight, somewhere in the Milky Way, a new star is igniting. A clump of gas has collapsed enough that nuclear fusion begins in its core. Hydrogen starts fusing into helium. Light begins to shine. A new sun is born. It will happen again tomorrow. And the day after. And every day for billions of years to come, until the galaxy finally runs out of gas, until the last star forms and the lights slowly go out. But that's far in the future. For now, the galaxy is still young, still vibrant, still creating. And it's not a one-way process. Stars don't just consume gas. They return it. When massive stars die, they explode as supernovae. These explosions are violent beyond imagining, briefly outshining entire galaxies, releasing more energy in a few seconds than the sun will emit in its entire lifetime. These supernovae blast the star's outer layers back into space at thousands of kilometers per second. The gas that was once locked in the star is freed, enriched now with heavy elements forged in the star's core and in the explosion itself. Carbon, oxygen, silicon, iron, gold, uranium. All the elements heavier than hydrogen and helium were made inside stars and distributed by supernovae. This ejected gas doesn't just drift away. It plows into the surrounding interstellar medium, creating expanding bubbles and shells. Multiple supernovae in the same region can create superbubbles, vast cavities in the galactic disk filled with hot, thin gas. Some of this hot gas is moving so fast that it escapes the disk entirely, fountain upward into the halo, rising hundreds or even thousands of light-years above the galactic plane. There, it cools, condenses, and eventually falls back down, raining back onto the disk like cosmic rain. This is called the galactic fountain, and it's one of the ways the galaxy mixes and recycles its material. Gas that forms stars in the disk is ejected by supernovae into the halo, then falls back to form new stars. The cycle continues, round and round, enriching the gas with each generation. Every atom of oxygen in your lungs passed through this cycle. It was forged in a massive star billions of years ago. That star exploded. The oxygen was blasted into space, drifted through the interstellar medium, condensed into a new molecular cloud, helped form the Sun and Earth, and eventually ended up in you. You are breathing recycled stardust. You are part of the galactic fountain. The dust between the stars is equally important. These microscopic grains, smaller than the particles in cigarette smoke, play a crucial role in star formation. They help cool molecular clouds by radiating away heat. They provide surfaces where molecules can form, and they're the seeds from which planets grow. In the disk around a young star, dust grains stick together, building up into pebbles, then rocks, then boulders, then asteroids, then planets. Earth formed this way 4.5 billion years ago, from countless tiny dust grains that collided and stuck together over millions of years. That dust came from dying stars. Old red giants, puffing off their outer layers in gentle stellar winds. Supernovae, condensing new grains in their cooling ejector. Each grain traveled for millions of years through interstellar space before ending up in the cloud that formed our solar system. Some of those grains still exist, unchanged, in primitive meteorites. Pre-solar grains, astronomers call them. Tiny specks of stardust older than the Sun, older than Earth, survivors from a previous generation of stars. We can hold them in our hands, study them in laboratories, read the history written in their atomic structures. The space between the stars is not empty. It's full of history, full of potential, full of the raw materials for everything that will ever exist. Gas and dust. Simple, humble substances. But from them, everything comes. Stars, planets, life. You. 10 to 15% of the galaxy's visible matter exists in this form, waiting. Some of it will form stars tomorrow. Some will drift for billions of years before finding a home. Some will eventually leave the galaxy entirely, expelled by supernova winds, lost to intergalactic space. But most of it will stay, cycling through stars, through space, through planets, through living things, round and round, forever changing form but never truly disappearing. The galaxy breathes, in a way. It inhales gas from the halo, forms stars, exhales enriched gas back into space. The cycle takes millions of years, but it's as steady and essential as your own breathing. In, out, creation, destruction, birth, death, return. 1 to 2 new stars per year. Each one a condensation of ancient gas. Each one carrying forward the legacy of all the stars that came before. And in some of those new stars, planets will form. And on some of those planets, given billions of years and extraordinary luck, life might arise. Life that will look up at the sky and wonder about the stars, about the gas and dust between them, about how it all came to be. Life like you. Made from the filling of the galaxy. Animated stardust. Conscious gas. The Orion Nebula glows tonight, 1,500 light-years away, birthing stars that will shine long after humanity is gone. Molecular clouds drift through the spiral arms, dark and cold and patient, waiting for gravity to pull them into new shapes, new suns, new worlds. The galactic fountain rises and falls, carrying enriched gas from the disk to the halo and back again, mixing, recycling, never wasting, never stopping. And you, lying here, are part of it all. Part of the cycle. Part of the fountain. Part of the eternal recycling of matter through the galaxy. Rest now. The nebulae will keep glowing. The clouds will keep collapsing. The stars will keep forming. The galaxy is full, and you are part of its fullness. Breathe in the recycled breath of ancient stars. Breathe out your own small contribution to the cosmic cycle. In, out. Like the galaxy itself. You are made of the same substance as nebulae, as molecular clouds, as the space between stars. The filling of the galaxy flows through you. And you are beautiful. The cycle continues. And you are held in its eternal turning. Everything that lives must die. This is true for mayflies and mountains, for civilizations and stars, for you and for galaxies themselves. But in the cosmos, death is never truly the end. It's transformation, recycling, return. Let's talk about the life cycles within the Milky Way. The birth, aging, and death of stars. The way clusters form and dissolve. The way matter flows from one generation to the next, carrying forward the story of everything that came before. Orbiting through the halo of the galaxy, tracing enormous elliptical paths that carry them high above and below the galactic disk, are the globular clusters. There are over 150 of them associated with the Milky Way. Each one is a dense, spherical collection of stars, anywhere from tens of thousands to millions of stars packed into a region just tens of light years across. If you lived on a planet in a globular cluster, your night sky would be breathtaking. Thousands of stars brighter than Venus, filling the darkness with light. No true night, just a perpetual twilight, the sky crowded with suns. These clusters are ancient, profoundly ancient. Most of them formed 10 to 13 billion years ago, in the early days of the galaxy, when the Milky Way was still taking shape. They're survivors from the beginning, witnesses to nearly the entire history of our galaxy. The stars in globular clusters are old, red, dim. All the massive, bright stars died long ago. What remains are the long-lived low-mass stars, red dwarfs and orange dwarfs that burn their fuel slowly, economically, stars that can shine for tens of billions of years. These clusters orbit through the halo on paths that take them far from the galactic disk. Some dive in close to the center, then swing back out, taking hundreds of millions of years to complete one orbit. They're nomads, wanderers, separate from the younger population in the disk. Studying globular clusters tells us about the galaxy's youth. The chemical composition of their stars reveals what the universe was like when they formed. Low in heavy elements, because there hadn't been many generations of stars yet to enrich the gas with carbon and oxygen and iron. These are second-generation stars, formed from gas that had been through only one or perhaps two cycles of stellar birth and death. They're ancient archives, libraries written in starlight. By reading them carefully, we can reconstruct the early history of the Milky Way, understand how it formed, how it grew. But globular clusters are dying, slowly. Stars occasionally escape, pulled away by tidal forces during close passes with the galactic disk or encounters with massive gas clouds. Over billions of years, the clusters gradually lose members, growing smaller, fainter, until eventually they dissolve completely. It takes a long time. Globular clusters are gravitationally bound tightly enough to survive for many billions of years. But they're not immortal. Given enough time, even these ancient survivors will fade away. In the disk, a different kind of cluster exists. Open clusters. These are much younger, much looser collections of stars. A few hundred to a few thousand stars, born together from the same molecular cloud, still loosely associated by their common origin and weak gravitational bonds. The Pleiades, visible to the naked eye as a small dipper of bright blue stars, is an open cluster. It's only about 100 million years old, incredibly young by cosmic standards. Its stars are still burning hot and bright, still close together, still recognizable as a group. But open clusters don't last. The gravitational bonds holding them together are weak. Encounters with other stars, with gas clouds, with the tidal forces of the galaxy itself, gradually pull them apart. Stars drift away, dispersing into the general population of the disk. Most open clusters dissolve within 100 to 200 million years. A few last longer, but eventually, inevitably, they come apart. The stars continue their individual orbits around the galaxy, no longer recognizably connected to their siblings, scattered across the disk like children grown up and moved away from home. Our Sun was born in an open cluster 4.6 billion years ago. Its siblings are still out there somewhere, scattered across the galaxy, unrecognizable now, mixed in with billions of other stars. We might never identify them. They're lost to time, to distance, to the slow dissolution that comes to all open clusters. But their material lives on. And that's what matters. Stars themselves have life cycles. They're born, they live, they die. The details depend on their mass, but the pattern is always the same. Low-mass stars, like red dwarfs, live the longest. They burn their hydrogen fuel so slowly, so carefully, that they can shine for trillions of years. The smallest red dwarfs will outlive the current age of the universe many times over. None of them have died yet. Every red dwarf that's ever been born is still shining. Medium-mass stars, like our Sun, live for billions of years. They spend most of their lives fusing hydrogen into helium in their cores, stable and steady, main sequence stars, reliable and predictable. But eventually, the hydrogen runs out. The core contracts, heats up, and helium fusion begins. The star swells into a red giant, growing hundreds of times larger, its outer layers becoming tenuous and cool while the core burns ever hotter. In about 5 billion years, this will happen to our Sun. It will swell to engulf Mercury, perhaps Venus, maybe even Earth. Its outer layers will puff off into space, creating a planetary nebula, a beautiful shell of glowing gas expanding outward. And at the center, the core will contract into a white dwarf, a dense ember the size of Earth but containing half the mass of the Sun. White dwarfs don't burn. They have no fuel left. They simply cool, radiating away their stored heat over billions of years, fading from white to yellow to red to eventually, after an unimaginably long time, black. Dark, cold, dead. But before they fade, stars in a particular phase, called the asymptotic giant branch, enrich the galaxy tremendously. These are red giants in their final stages, pulsing and unstable, dredging up heavy elements from their cores and blowing them off into space in stellar winds. Carbon, nitrogen, oxygen, elements created by fusion in the star's interior, now returned to the interstellar medium. Half of all the carbon in the galaxy comes from asymptotic giant branch stars. The carbon in your DNA, in every organic molecule in your body, was made inside these dying stars and expelled into space to be recycled into new stars, new planets, new life. They're generous in their death, these stars. They give back everything they made, everything they learned, everything they became. White dwarfs, once formed, cool slowly. So slowly that we can use them as cosmic clocks. By measuring the temperature of white dwarfs in a cluster, we can determine how long they've been cooling, which tells us how long ago the cluster formed. The coolest, dimmest white dwarfs in the Milky Way's halo are about 12 to 13 billion years old. This sets a lower limit on the age of the galaxy. The Milky Way must be at least as old as its oldest white dwarfs, probably a bit older. These ancient embers, barely glowing, nearly invisible, are timestamps. They remember the early universe. They mark the passage of billions of years in their slow fade from light to darkness. Massive stars live differently. They burn bright and die young. A star 10 times the mass of the Sun might live only 20 million years. A star 50 times the mass of the Sun, just a few million years. They race through their life cycles, fusing hydrogen, then helium, then carbon, then oxygen, building up heavier and heavier elements in their cores, like an onion with layers of different elements. And then, when they've fused everything they can, when they've built up an iron core that can't be fused further, they collapse. The core implodes in a fraction of a second. The outer layers rebound off the collapsing core and explode outward. A supernova. A catastrophic death that outshines billions of normal stars. In that explosion, in the tremendous energies involved, elements heavier than iron are created. Gold, platinum, uranium. These can only form in supernovae or in collisions between neutron stars. Every gold atom in every ring, every coin, every circuit board, was forged in such an explosion billions of years ago. The remnant of the star, if it's massive enough, becomes a neutron star or even a black hole. A neutron star is a city-sized ball of matter so dense that a teaspoon of it would weigh billions of tons. It spins rapidly, sometimes hundreds of times per second, pulsing like a cosmic lighthouse. Or, if the star was massive enough, it collapses completely into a black hole, joining the population of stellar mass black holes scattered throughout the galaxy. The Milky Way probably contains about 100 million stellar mass black holes, most of them invisible, detectable only when they're actively feeding or when they orbit another star closely enough to affect its motion. Birth from clouds. Life burning fuel. Death returning material to space. The cycle is perfect, elegant, inevitable. Open clusters form, dissolve, scatter their stars. Globular clusters orbit through the halo, slowly fading, losing members one by one. Red giants pulsate and shed their outer layers. White dwarfs cool into darkness. Massive stars explode, seeding the galaxy with heavy elements. Every stage serves a purpose. Every death enables new births. The matter cycles through, never created, never destroyed, only transformed, only rearranged into new patterns, new forms, new possibilities. You are part of this cycle. The calcium in your bones came from an exploding star. The iron in your blood was forged in a supernova. The oxygen you breathe was made in the core of a massive star and expelled in its death throes. You are the endpoint, for now, of countless stellar life cycles. You are what the universe becomes when it learns to think, to feel, to wonder about itself. And one day, billions of years from now, the atoms that make up your body will be recycled too. Perhaps into new planets. Perhaps into new life. The cycle will continue, long after you, long after humanity, long after Earth itself has been reclaimed by the cosmos. But tonight, now, you are here. A temporary arrangement of recycled stardust, briefly organized into the complex pattern that is you. The globular clusters orbit on, ancient and patient. The open clusters form and dissolve, young and fleeting. The stars cycle through their lives, from birth in molecular clouds to death as white dwarfs or neutron stars or black holes. And you rest here, breathing slowly, part of it all, connected to everything through the shared substance of the universe. Birth, life, death, transformation, return. The galaxy knows this rhythm. It's been dancing to it for 13 billion years. And tonight, you dance too, though your steps are small and brief compared to the cosmic waltz of stars. The life cycles continue without your attention. Stars are being born. Stars are dying. Matter is being recycled, transformed, reborn. You are part of the transformation. You are part of the eternal return. You are made of lives and deaths beyond counting. The cycle holds you. And one day, you will return to it, contributing your atoms to whatever comes next. The globular clusters wheel through the halo. The white dwarfs cool slowly in the darkness. The massive stars burn bright and brief. And you, temporary and precious, breathe and dream and wonder. The cycle continues. Always has. Always will. And you are part of its eternal beauty. The stars will handle their own deaths and births. You need only rest in the knowledge that you are made of their legacy. Breathe slowly. The cycle breathes with you. In and out. Birth and death. Light and darkness. All one rhythm. All one dance. And you, for this moment, are part of the music. The galaxy cycles on, carrying you gently through all its transformations. You are held. You are part of the pattern. The life of the galaxy continues. And you, briefly, beautifully, are part of that life. Most of the galaxy is calm, peaceful, even. Stars orbit quietly. Gas drifts slowly. Planets circle their suns in predictable patterns. The universe runs on gentle laws, on gradual processes that take millions or billions of years. But not everywhere. Not always. In some corners of the Milky Way, violence reigns. Extreme physics. Conditions so bizarre, so far removed from everyday experience, that they challenge our understanding of reality itself. Let's visit these extremes. Let's see what happens when the universe pushes matter and energy to their limits. Imagine a star moving so fast that it's leaving the galaxy. Not just orbiting quickly, but actually escaping, fleeing the Milky Way's gravitational pull at tremendous speed, destined to wander forever through intergalactic space. These are hypervelocity stars, and they exist. We've found them. Stars moving at up to 1,700 kilometers per second, more than 1,000 miles per second, fast enough to cross the entire United States in 3 seconds. At that speed, nothing can hold them. Not the galaxy's gravity, not the pull of the central black hole. They're gone, ejected, cast out into the void. How does this happen? How does a star get moving so fast? Most hypervelocity stars were born in binary systems near the galactic center. 2 stars orbiting each other, venturing too close to Sagittarius A star. The black hole's gravity captured one star, pulling it into a tight orbit, and flung the other away like a slingshot. The ejected star goes careening off into space, carrying tremendous kinetic energy, moving so fast that it will eventually leave the galaxy entirely and drift alone through the darkness between galaxies. Imagine that. Being a star, born in the crowded center of the galaxy, only to be cast out, exiled, sentenced to an eternity of solitude in the vast intergalactic void. No neighbors. No companion galaxies nearby, not for millions of light years. Just you, alone, burning in the darkness. Some hypervelocity stars will travel for hundreds of millions of years before finally escaping the Milky Way's outer halo. Others are already gone, already crossing into intergalactic space, already beyond recall. They're rare, these exile stars. We've only found a few dozen so far. But they remind us that even in a galaxy, there are outcasts. Even in a system as vast as the Milky Way, there are those who don't fit, who get thrown out, who end up wandering alone. Now imagine a magnetic field so strong that it would kill you from 1,000 miles away. Not by pulling on the iron in your blood, though it would do that too, but by disrupting the electromagnetic bonds between atoms in your body. The field would be so intense that molecular bonds would become unstable. You would simply come apart, your atoms pulled in different directions by magnetic forces stronger than the forces holding you together. This is a magnetar. A magnetar is a type of neutron star, a stellar remnant formed when a massive star explodes. But where a typical neutron star might have a magnetic field 1 trillion times stronger than Earth's, a magnetar's field is 1,000 times stronger still. 1,000 trillion times Earth's magnetic field. 1 quadrillion times. It's the strongest magnetic field in the known universe. Nothing else even comes close. These fields are so intense that they affect the vacuum of space itself. Quantum mechanics tells us that empty space isn't truly empty, that virtual particles are constantly popping into and out of existence. In a magnetar's magnetic field, these virtual particles become polarized, aligned, turning empty space into a birefringent medium, like a crystal that bends light differently depending on its polarization. Space itself becomes strange near a magnetar. The magnetic field stores tremendous energy. Sometimes, the field shifts, reconfigures, releases some of that energy in an event called a starquake. The neutron star's crust, made of crystallized nuclear matter, literally cracks under the magnetic stress. The shift in the magnetic field releases more energy in 1/10 of a second than the sun will emit in 100,000 years. These events produce gamma-ray bursts. Gamma rays are the highest energy form of light, far beyond X-rays, beyond ultraviolet. They're so energetic that individual photons can create matter when they collide, turning pure energy back into particles, running Einstein's equation backwards. When a magnetar produces a gamma-ray burst, it can briefly outshine the entire rest of the galaxy. Not the galactic core. The entire galaxy. All 400 billion stars. For a few seconds, one tiny neutron star, barely 10 miles across, emits more light than the combined output of everything else in the Milky Way. In December 2004, a magnetar called SGR 1806-20, located on the other side of the galaxy, 50,000 light-years away, produced a burst that briefly affected Earth's ionosphere. From 50,000 light-years away, across the entire width of the galactic disk, the burst was strong enough to measurably ionize Earth's upper atmosphere. If that magnetar had been just 10 light-years away, within the local neighborhood of nearby stars, the burst would have been catastrophic. It would have stripped away Earth's ozone layer. It might have caused a mass extinction. Fortunately, magnetars are rare. There are probably only about 30 of them in the entire galaxy. And they're all far away, safely distant. No threat to Earth or to any life that might exist elsewhere in the Milky Way. But they exist. They're real. And they remind us that the universe is capable of violence we can barely imagine. Some neutron stars aren't alone. They have companions, other stars orbiting them. And when a neutron star pulls matter from a companion star, something extraordinary happens. The matter spirals inward, forming an accretion disk around the neutron star. It heats up from friction, glowing in X-rays. And the neutron star's magnetic field channels some of this matter to the magnetic poles, where it slams into the surface at a significant fraction of the speed of light. The collision produces jets, beams of particles and radiation shooting out from the poles. These jets interact with the surrounding gas, creating expanding bubbles called pulsar wind nebulae. These nebulae glow intensely in radio waves and X-rays. They're beautiful when seen through the right telescopes. Intricate structures, filaments, and wisps and shells, all powered by the incredible energy output of the central neutron star. The Crab Nebula is the most famous example. At its center sits a pulsar, a neutron star spinning 30 times per second, blasting out a wind of particles that inflates the surrounding nebula. The nebula glows across the electromagnetic spectrum, from radio waves to gamma rays, all powered by the rotational energy of that tiny spinning star. Pulsar wind nebulae are particle accelerators on a cosmic scale. Electrons in the wind are accelerated to nearly the speed of light, their energies far exceeding anything we can produce in our most powerful particle colliders on Earth. These are laboratories for extreme physics, places where we can study matter and energy in conditions we'll never be able to recreate artificially. And then there are the hypotheticals. The objects we think might exist, but haven't confirmed yet. Thorne-Zitko objects. Named after the physicists who predicted them, Kip Thorne and Anna Zitko. These would be hybrid stars, bizarre chimeras, red supergiants with neutron stars at their cores. How would such a thing form? Imagine a binary system where one star explodes as a supernova, leaving behind a neutron star. That neutron star continues orbiting its companion. Over time, the two stars spiral inward, drawn together by gravitational radiation, until eventually the neutron star spirals into the envelope of the giant companion. Instead of destroying the companion, the neutron star sinks to its center and stays there, sitting at the heart of the giant star like a pit inside a fruit. The result is a star with two layers. A normal stellar envelope, fusing hydrogen into helium, and at the very center, a neutron star, so dense that a teaspoon of it would weigh as much as a mountain. The neutron star would heat the surrounding material, affecting the star's evolution, changing its chemical composition in distinctive ways. By looking for stars with unusual elemental abundances, we might be able to identify Thornzico objects. We've found a few candidates. Stars that don't quite fit the normal patterns, that have too much of certain elements and too little of others. But we're not certain yet. They might be Thornzico objects. They might be something else entirely. The universe has room for strangeness. For objects we haven't imagined yet. For combinations of matter and energy that push physics to its limits. Hypervelocity stars fleeing the galaxy. Magnetars with fields that warp space itself. Gamma-ray bursts that briefly outshine billions of stars. Pulsar wind nebulae where particles race at near-light speeds. Possible hybrid stars with neutron stars at their hearts. These extremes exist. They're real. They're happening right now, somewhere in the Milky Way. But they're far away. Safely distant. The galaxy is vast enough that these violent events rarely affect anything else. The extreme regions are isolated, contained, no threat to the calm suburbs where we live. You can rest easy knowing that while the universe is capable of tremendous violence, it's also capable of sheltering gentle places. Places where stars shine steadily for billions of years. Where planets orbit peacefully. Where life can emerge and evolve and wonder about the extremes without being touched by them. The weird and violent corners of the galaxy are reminders that physics has no limits, that matter and energy can be pushed to unimaginable extremes. But they're also reminders that most of the galaxy is nothing like that. Most of the galaxy is calm, stable, safe. We live in the calm regions. The fortunate regions. The places where extremes are distant stories, fascinating but not threatening. Tonight, no hypervelocity stars threaten Earth. No magnetar bursts ionize our atmosphere. No pulsar wind nebula expands toward us. We are safe in our quiet corner, 27,000 light-years from the center, far from the violence, far from the chaos. The extremes exist, but they don't define the galaxy. They're the exception, not the rule. The magnetars spin on, safely distant. The hypervelocity stars race away, leaving us behind. The pulsar wind nebulae glow in wavelengths we can't see, far away, beautiful and terrible and harmless at this distance. The galaxy contains multitudes. Calm and chaos. Gentle and violent. Familiar and bizarre. And you, lying here, are in the gentle part. The safe part. The part where stars live long and planets remain stable and life has time to develop, to grow, to think, to dream. The extremes are far away. The violence is contained. The weird corners of the universe can wait until morning. You are held in the calm regions of the galaxy. And that is a gift beyond measure. Breathe slowly. The magnetars can't reach you. The hypervelocity stars are leaving, not approaching. The gamma-ray bursts happen far, far away. You are safe. You are home. You are in the peaceful suburbs of the Milky Way. And here, in the peace, here, there is only calm. Only quiet. only the gentle turning of ordinary stars in their ordinary orbits. And you, ordinary and extraordinary all at once, breathing slowly, settling into sleep. The galaxy holds both violence and peace. And tonight, it offers you the peace. Accept it. Rest in it. Let it carry you into dreams. Nothing in the galaxy stands still. Everything moves. Everything spins, orbits, oscillates, dances through space according to laws written in gravity and momentum. But the motion isn't simple. It's not just stars circling the center in neat circles like planets around the sun. It's more complex than that. More beautiful. More strange. Let's talk about motion. About the hidden forces that shape how everything moves. About the invisible architecture that keeps the galaxy organized despite hundreds of billions of stars all moving independently. When astronomers first tried to measure how fast stars orbit the galactic center at different distances, they expected a simple pattern. Close to the center, where most of the mass is concentrated, stars should move fast. Farther out, where there's less mass, they should move slower, just like planets in our solar system. Mercury orbits quickly. Neptune crawls. That's what Newton's laws predict. That's what should happen. But that's not what we see. Instead, the rotation curve stays flat. Stars at 60,000 light-years from the center move just as fast as stars at 30,000 light-years. Even farther out, at the very edges of the visible disk, the rotation speed barely decreases. This shouldn't be possible. There isn't enough visible matter to explain it. The stars and gas we can see don't have enough mass to produce the gravity needed to keep those outer stars moving so fast. And yet, they do move that fast. The observations are clear, repeated, confirmed. The rotation curve is flat. This was one of the first clear pieces of evidence for dark matter. Something invisible is out there, something with mass, something creating gravity. It forms a halo around the galaxy, extending far beyond the visible stars, and its gravity keeps the outer regions rotating faster than they should. The dark matter halo is real. We can't see it, can't touch it, barely understand what it is. But we can see its effects. We can see how it shapes the motion of everything in the galaxy. Without dark matter, the Milky Way would fly apart. The outer stars would escape into space. The galaxy would gradually dissolve, losing its structure, its shape, its coherence. But the dark matter holds it together. Invisible hands, keeping everything in place, maintaining the flat rotation curve, preserving the spiral structure. You're moving through this dark matter halo right now. Earth is. The sun is. We're swimming through it, though it doesn't interact with us in any way we can detect. It passes through us like we're not even there, like ghosts passing through walls. And yet, it holds the galaxy together. It keeps us in our orbit. It maintains the structure of everything. The spiral arms themselves are sustained by something equally invisible, though not as mysterious. Density waves. The arms aren't rigid structures. Stars move through them the way cars move through a traffic jam. The jam stays in place while the cars pass through. The spiral arms stay in place while stars orbit in and out of them. These density waves are maintained by resonances, specific orbital radii where the natural frequency of stellar orbits matches the rotation rate of the spiral pattern. These are called Lindblad resonances, named after the Swedish astronomer who first described them. At these resonance points, stars feel periodic gravitational nudges that reinforce the spiral structure. It's like pushing a child on a swing. Time it right, push at the resonance frequency, and the swing goes higher and higher with minimal effort. Push at the wrong time, and nothing happens. The galaxy pushes at just the right time, at just the right places, and the result is stable spiral arms that persist for billions of years even though the material in them is constantly changing. It's an elegant solution. A way to maintain structure without rigidity. a pattern that persists even as everything within it flows and changes. The motion of stars isn't confined to the flat disk, either. They bob up and down as they orbit. These are vertical oscillations, and they can carry stars up to 1,000 light-years above or below the galactic midplane. The Sun itself is currently about 50 light-years above the midplane, moving upward. In another 15 million years or so, we'll reach maximum height, then start falling back down, crossing through the midplane and continuing down the other side. This bobbing motion has a period of about 60 to 70 million years. We complete one full oscillation, up and down and back to the starting point, about 3 or 4 times per orbit around the galactic center. Some scientists have speculated that our passages through the denser regions of the galactic plane might trigger comet showers from the Oort cloud, potentially causing periodic mass extinctions. The evidence is debated. The theory is controversial, but it's a reminder that our motion through the galaxy might matter more than we realize. The oscillations are caused by the gravitational pull of the disk itself. As a star moves above the plane, the disk's gravity pulls it back down. It crosses the mid-plane, still moving downward, and continues until the disk's gravity slows it, stops it, and pulls it back up again. It's like a weight on a spring, bouncing up and down, never quite coming to rest. The galaxy is full of these oscillations, billions of stars all bobbing at slightly different phases, creating a thick disk rather than a razor-thin plane. And the orbits themselves aren't simple circles. They're epicycles. An epicycle is an orbit within an orbit, a small loop traced out as a star moves around the galaxy. From a rotating reference frame fixed on the star's average position, the star appears to trace out a small ellipse, circling this average position as it moves around the galactic center. It's the same kind of motion that puzzled ancient astronomers when they tried to understand planetary motion from Earth's perspective. Planets seemed to move in loops against the background stars, advancing, then temporarily reversing, then advancing again. Epicycles. We now know that planetary epicycles are just artifacts of observing from a moving platform. But stellar epicycles in the galaxy are real orbital features, caused by the way gravity works in a rotating disk. These epicyclic motions mean that stars don't stay at constant distances from the galactic center. They move in and out slightly, tracing complex rosette patterns over millions of years. Our Sun's orbit isn't a perfect circle. It varies between about 25,000 and 28,000 light-years from the center as we go around. This complexity, these epicycles and oscillations and resonances, they all combine to create the rich, intricate structure of the galaxy. Nothing moves simply. Everything is coupled to everything else through gravity, through resonances, through density waves. At the galactic center, the central bar rotates, and its gravity creates additional resonances. These bar resonances affect the orbits of stars in the inner galaxy, trapping them in specific patterns. The result is an X-shaped bulge, visible when we look at the galaxy edge-on in infrared light. The bar and its resonances have organized the central stars into this distinctive shape, a bright X extending above and below the galactic plane. It's another example of how gravity and motion create structure. The bar didn't consciously design an X shape. It's just physics, playing out over billions of years, organizing chaos into pattern. The galaxy is a gravitational symphony. Every star is an instrument, playing its note, moving in its orbit. The dark matter provides the baseline, deep and steady, holding everything together. The spiral arms are the melody, rising and falling, persistent yet flowing. The oscillations and epicycles are harmonics, adding complexity and richness to the sound. And it all works. Somehow, despite the complexity, despite billions of independent objects all moving according to simple laws, it creates coherent structure. Spirals, bars, arms, a recognizable galaxy shape that persists for billions of years. You're part of this motion. Right now, you're orbiting the galactic center at 550,000 miles per hour. You're bobbing upward through the galactic plane at 10,000 miles per hour. You're tracing out an epicycle, moving slightly closer to the center and then slightly farther away as the sun completes its reset orbit. You can't feel any of it. It's too smooth, too constant. You feel still, at rest, motionless. But you're dancing. The whole solar system is dancing. The whole galaxy is dancing. And the choreography is provided by gravity, by resonances, by the invisible hand of dark matter, by the subtle interplay of forces that we're only beginning to fully understand. The motion continues whether you think about it or not. The rotation curve stays flat. The Lindblad resonances maintain the spiral arms. The vertical oscillations carry stars up and down. The epicyclic motion traces complex paths through space. The bar resonances shape the central bulge. All of it happening simultaneously, all of it interconnected, all of it creating the living, breathing, moving structure we call the Milky Way. Rest now. Let the motion carry you. You don't need to steer. The galaxy knows where it's going. The orbits are stable. The forces are balanced. You are held in invisible hands, guided by dark matter, shaped by resonances, carried by momentum that has persisted for billions of years. The galaxy moves, and you move with it. Always have. Always will. Breathe slowly. Feel how still you are, even as you race through space. Feel how solid the Earth is beneath you, even as it orbits and spins and moves through the galaxy. Motion and stillness are the same thing, depending on your perspective. Relative to the galaxy, you're moving at tremendous speed. Relative to yourself, you're perfectly still. Both are true. Both are real. The hidden forces work their magic. The dark matter holds. The resonances maintain structure. The orbits persist. And you, small and brief, are part of the grand motion. Part of the galactic dance that has continued for 13 billion years. Most of what exists, you cannot see. This is one of the most profound revelations of modern astronomy. Not just that there are things too far away or too faint to see, but that most of the universe is fundamentally invisible. Not hidden by distance or darkness, but invisible by nature. Made of something that doesn't interact with light at all. We've mentioned dark matter already, but let's sit with it now. Let's really try to understand what it means that most of the galaxy, most of the universe, is made of something we cannot see, cannot touch, cannot directly detect. It's humbling, and beautiful, and deeply mysterious. The evidence is overwhelming. When astronomers measure how fast stars orbit at different distances from the galactic center, the speeds are wrong. Too fast. Stars in the outer regions are moving so quickly that they should escape the galaxy's gravity and fly off into space. But they don't. They stay in orbit, held by something we cannot see. That something is dark matter. An invisible substance, perhaps 5 or 6 times more massive than all the stars, gas, and dust combined. It forms a vast halo around the galaxy, extending far beyond the visible disk, and its gravity holds everything together. We know it's there. We can measure its effects precisely. But we don't know what it is. It's not ordinary matter. Not protons and neutrons and electrons. It doesn't form atoms, doesn't emit light, doesn't absorb light, doesn't reflect light. Light passes through it as if it weren't there at all. It interacts only through gravity. That's all. Its presence warps space-time, pulling on things, holding galaxies together, but otherwise it's a ghost, undetectable except for its gravitational influence. Scientists have built incredibly sensitive detectors, buried deep underground to shield them from cosmic rays and other interference, trying to catch a dark matter particle as it passes through Earth. So far, nothing. No confirmed detections. Just upper limits on what it isn't. Dark matter passes through you right now. Billions of particles every second, streaming through your body, through the earth, through everything, interacting with nothing, leaving no trace. You are transparent to it. It is transparent to you. Two kinds of matter, occupying the same space, barely aware of each other's existence. And yet, without it, the galaxy wouldn't exist. Without dark matter's gravity, the gas clouds that formed the first stars would have dispersed. Galaxies would never have condensed. Structure would never have formed. The universe would be a thin, uniform soup of hydrogen and helium, expanding forever, never collapsing into anything interesting. Dark matter is the scaffolding upon which visible matter builds. It's the invisible frame that allows stars and galaxies to exist. There's another mystery at the galactic center. A persistent glow of gamma rays, the highest energy photons, emanating from the central regions of the Milky Way. This gamma ray excess, as astronomers call it, is puzzling. It's brighter than expected. The known sources, pulsars and supernova remnants and cosmic ray interactions, can't fully account for it. One possibility, one tantalizing explanation, is that we're seeing dark matter annihilation. If dark matter particles are their own antiparticles, they can annihilate when they meet, converting their mass into pure energy. Gamma rays. The process would be rare, requiring two dark matter particles to collide in the vastness of space, but in the dense central regions of the galaxy, where dark matter is concentrated, it might happen often enough to produce a detectable glow. We're not certain. The gamma ray excess could be explained by ordinary astrophysics we don't fully understand yet. Pulsars we haven't detected. Cosmic ray interactions we haven't modeled correctly. It's too early to claim we've seen dark matter annihilation. But the possibility is there. The data is consistent with it. We might be seeing dark matter particles meeting and converting into light, a faint glow from the invisible substance that holds the galaxy together. Imagine that. Dark matter, invisible by nature, occasionally revealing itself through these rare annihilations, these tiny flashes of gamma rays at the galactic center. The invisible made briefly, faintly visible. We're still investigating, still trying to understand. The universe keeps its secrets close, and there may be even more invisible things out there. Entire galaxies we haven't found yet. Dwarf galaxies, small collections of stars and dark matter, orbit the Milky Way. We've found dozens of them, small satellites gravitationally bound to us, circling through the halo. The Large and Small Magellanic Clouds are the largest and most famous. Others are much smaller, fainter, harder to find. But theory predicts there should be hundreds of dwarf galaxies orbiting us. Maybe thousands. Where are they? Some might be too faint to see. So-called ultra-faint dwarfs, containing just a few thousand stars, spread out over hundreds of light-years, barely glowing at all. We've found a few of these in recent years, but there are probably many more, waiting to be discovered. Others might be dark galaxies. Collections of dark matter with very few or even no stars at all. Just invisible halos of dark matter, orbiting through space, completely undetectable except through their gravitational effects on other objects. How do you find an invisible galaxy? It's not easy. You look for gravitational effects. Distortions in the light from background galaxies, gravitational lensing caused by the dark galaxy's mass. Or you look for the faint glow of any gas that might be associated with it, heated by shocks or radiation. It's difficult work, like trying to find black cats in a dark room. But astronomers are persistent. And every few years, they find another ultra-faint dwarf, another ghostly companion to the Milky Way. The galaxy is not alone. It's surrounded by a cloud of smaller galaxies, most of them too faint to see easily, some perhaps completely invisible. Our gravitational family, our satellites, our companions. And some of these companions have already died. When a small galaxy ventures too close to the Milky Way, our tidal forces tear it apart. Its stars are stripped away, one by one, forming long streams that wrap around our galaxy like ribbons. These are stellar streams, and they're visible if you know how to look for them. Long, thin arcs of stars, all moving together through space, all following similar orbits, all tracing the path their parent galaxy took as it was destroyed. The streams are fossils, archaeological evidence of ancient galactic cannibalism. By studying them, we can reconstruct the history of the Milky Way's meals, identify which dwarf galaxies we've consumed, understand how our galaxy grew. Some streams are relatively young, just a few billion years old, still coherent and easy to identify. Others are ancient, dispersed, mixed into the general stellar population, barely recognizable. But they're there, ghosts of dead galaxies. Their stars now part of the Milky Way but still remembering, through their orbits, where they came from. The Sagittarius stream is one of the most prominent. It wraps completely around the galaxy, a river of stars stripped from the Sagittarius dwarf elliptical galaxy over the past few billion years. That galaxy is still there, still orbiting us, but it's being shredded. In another few billion years, it will be gone completely, its stars scattered throughout the Milky Way, just another contribution to our ever-growing mass. These streams are everywhere, if you look carefully. Thin threads of stars, barely visible against the background of the galaxy, but they're traceable, evidence of destruction and assimilation. The invisible shapes the visible. Dark matter holds galaxies together. Gamma ray glows hint at particle annihilation. Unseen dwarf galaxies orbit in the darkness. Stellar streams trace the paths of galaxies that no longer exist. Most of the story is hidden. Most of the galaxy is invisible. We see only a fraction of what's there. And yet, from that fraction, we can infer so much. We can deduce the existence of dark matter. We can predict unseen satellite galaxies. We can trace the ghostly streams of dead companions. The invisible leaves traces, clues, hints of its presence. You live in a universe where most things are hidden, where the majority of matter is fundamentally undetectable, where entire galaxies might exist unseen, where the forces holding everything together are invisible. It's like living in a house where most of the walls are transparent. You can see through them, but they're there, supporting the roof, dividing the rooms, giving structure to everything. Dark matter is those invisible walls. Essential, real, but fundamentally beyond your direct perception. And that's okay. You don't need to see it to benefit from it. You don't need to touch it to be held by it. The galaxy is held together by things you cannot see. And you are part of what it holds. Dark matter surrounds you, passes through you, holds the galaxy together around you. You cannot feel it, but it's there. Dwarf galaxies orbit in the darkness, too faint to see with your eyes, but real nonetheless. Stellar streams wind through the halo, ghosts of ancient companions, traces of the galaxy's violent past. And perhaps, at the galactic center, dark matter particles occasionally meet and annihilate, producing a faint gamma-ray glow, the invisible made briefly visible, a whisper from the hidden majority of the universe. Most of what exists, you cannot see. But it's there, supporting you, holding you, shaping the universe you inhabit. The visible is just the tip. Beneath it lies a vast invisible realm, dark matter and dark galaxies and streams of stars from dead companions, all of it part of the larger structure, all of it essential. You are held by the invisible. You always have been. The dark matter halo cradles the galaxy, and the galaxy cradles you. You are surrounded by mysteries, by invisible forces, by things that exist but cannot be seen. And that's beautiful. The universe has depths beyond what eyes can perceive, layers beyond what instruments can detect. mysteries that may never be fully solved. The Milky Way is not alone. It never has been. We tend to think of it as a single entity, our galaxy, a self-contained island of stars floating in the cosmic ocean. But that's not quite right. The Milky Way is part of a family. It has companions, satellites, neighbors. It exists in context, in relationship with other galaxies. And understanding those relationships helps us understand our home. Orbiting the Milky Way, bound to us by gravity, circling through the halo on long elliptical paths, are over 50 satellite galaxies. 50. More than 50 separate galaxies, each with its own stars, its own history, its own story, all gravitationally tied to us, all part of the Milky Way system. Most of them are dwarf galaxies, small and faint. Some contain just a few thousand stars, barely more than a large globular cluster. Others have millions of stars, still tiny compared to the Milky Way's hundreds of billions, but substantial in their own right. These satellites are family. They orbit us like moons orbit a planet, like planets orbit the sun. We're the dominant mass, the gravitational anchor, and they circle us, some taking billions of years to complete one orbit. They're not all at safe distances. Some venture close, too close, and when they do, our tidal forces begin to tear them apart. Their outer stars are pulled away, forming those stellar streams we talked about earlier. The satellite shrinks, loses mass, and if it survives, it swings back out into the halo to orbit again, diminished, wounded. Others won't survive. They'll be completely consumed, their stars scattered and mixed into the Milky Way, absorbed, assimilated, made part of us. This is how galaxies grow. Not just by forming new stars from gas, but by consuming smaller galaxies, by cannibalizing their companions. It sounds violent, and in a way it is, but it happens so slowly, so gently, that individual stars are almost never affected. They just find themselves with a new address, citizens of a different galaxy than the one they were born in. The largest and most famous satellites are the Magellanic Clouds. If you're in the southern hemisphere, on a clear night far from city lights, you can see them with your naked eyes. Two fuzzy patches of light, like detached pieces of the Milky Way, floating separately in the sky. The large Magellanic Cloud and the small Magellanic Cloud. Named after Ferdinand Magellan, whose expedition noticed them while sailing through southern waters in the early 1500s, though indigenous peoples of the southern hemisphere had known about them for thousands of years, of course, woven them into their myths and stories. The large Magellanic Cloud is about 160,000 light-years away. The small Magellanic Cloud is about 200,000 light-years distant. They're our closest galactic neighbors, and they're spectacular. The large Magellanic Cloud is irregular in shape, distorted by its interactions with us and with the small Magellanic Cloud. It contains about 30 billion stars, maybe a tenth of the Milky Way's population. It's actively forming stars, particularly in a region called the Tarantula Nebula, one of the most vigorous star-forming regions known, a nursery so active and so bright that if it were as close as the Orion Nebula, it would cast shadows on Earth at night. The small Magellanic Cloud has about 3 billion stars, smaller and fainter, also irregular in shape, also distorted by gravitational interactions. Both clouds are connected by a stream of gas, the Magellanic Stream, stripped from them by their interactions with each other and with the Milky Way. This stream wraps around our galaxy, a ribbon of neutral hydrogen gas stretching across more than 200 degrees of sky, evidence of the ongoing gravitational dance between us and our companions. The Magellanic Clouds are orbiting us, but their orbits are being affected by dynamical friction, the gravitational drag from the Milky Way's dark matter halo. Over billions of years, their orbits will decay. They'll spiral inward. Eventually, perhaps 4 to 5 billion years from now, they'll merge with the Milky Way completely. When that happens, there will be a burst of star formation as their gas collides with ours. New stars will light up, bright and blue and beautiful. And the Magellanic Clouds, as separate entities, will cease to exist. Their stars will become our stars. Their gas will become our gas. But for now, they're still independent. Still satellites. Still companions orbiting at a safe distance, visible from Earth's southern hemisphere. Beautiful reminders that the Milky Way exists in context, in relationship. Much closer, and in much more immediate danger, is the Sagittarius dwarf elliptical galaxy. This small galaxy is only about 70,000 light-years from the galactic center, well within our halo, and it's being torn apart as we speak. The Sagittarius dwarf has already made several passes through the Milky Way's disk. Each time it crosses, our tidal forces strip away more of its stars. Long streams of these stars wrap around our galaxy in multiple loops, tracing the dwarf's orbital path over the past few billion years. The galaxy itself, what remains of it, is still detectable. Still coherent enough to be recognized as a separate entity. But it's dying. In another orbit or two, perhaps a billion years from now, it will be completely disrupted. Its stars will be scattered throughout the Milky Way, indistinguishable from our own. We're watching a galaxy die in slow motion. Watching it be consumed by our gravity, torn apart, dissolved. It's been happening for billions of years, and it will continue for billions more, until finally, nothing remains but streams of stars and the memory of what once was a separate galaxy. There's something melancholy about that. This small galaxy, orbiting too close, unable to escape, slowly being destroyed by forces beyond its control. Its stars didn't choose this fate. They were simply born in a small galaxy that happened to orbit too near a larger one. But in another sense, those stars aren't dying. They're joining us, becoming part of something larger. Their atoms will continue to exist, to shine, to be part of the cosmic story. Just under a different flag, so to speak. And there's evidence of even larger past meals. The Virgo overdensity is a region of the galactic halo with more stars than expected. A clumping, a concentration, spread over a large area of sky. It was discovered in the early 2000s when astronomers carefully mapped the density of stars in different parts of the halo. This overdensity is probably the remnant of a massive merger, a large dwarf galaxy that the Milky Way consumed billions of years ago. The galaxy is gone, completely disrupted, but its stars remain, still concentrated in the region where the collision occurred, still carrying the memory of their origin in their positions and velocities. By studying structures like the Virgo overdensity, astronomers can reconstruct the Milky Way's merger history. Who did we eat? When? How massive were they? What did they contribute to our current structure? It turns out the Milky Way has had a violent past. Multiple major mergers in the first few billion years of its existence. The galaxy grew by consuming others, by absorbing their stars and gas, by building itself up through cannibalism. The smooth disk we see today, the organized spiral structure, it all emerged from chaos. From mergers and collisions and disruptions. Gradually, over billions of years, things settled down. The gas formed a disk. Stars organized into spiral arms. The violence of youth gave way to the relative calm of middle age. But the evidence of that violent past remains. In stellar streams. In overdensities. In the chemical compositions and velocities of stars that don't quite fit the main population, that betray their origins in galaxies that no longer exist. The Milky Way is built from other galaxies. We are an amalgamation, a collection, a synthesis of everything we've consumed over 13 billion years. And the process continues. The Sagittarius dwarf is being absorbed right now. The Magellanic Clouds will be absorbed in the future. Other small satellites will eventually venture too close and meet the same fate. We're still growing. Still accumulating mass. Still adding to our stellar population through cannibalism. But we're not just a consumer. We're also part of a larger structure. The Milky Way and Andromeda, along with the Triangulum Galaxy and about 50 smaller dwarf galaxies, form the local group. We're all gravitationally bound together, orbiting our common center of mass, a small galactic family in the vast universe. And the local group itself is being pulled toward the Virgo supercluster, a massive collection of galaxy clusters about 65 million light-years away. We're falling toward it, very slowly, drawn by its enormous gravity. Context within context within context. The Milky Way has satellites. The Milky Way is part of the local group. The local group is part of the Virgo supercluster. The Virgo supercluster is part of an even larger structure called Laniakea, a supercluster of superclusters, containing about 100,000 galaxies. Everything is connected. Everything is part of something larger. Nothing exists in isolation. You are on Earth. Earth orbits the Sun. The Sun orbits the Milky Way. The Milky Way is surrounded by satellite galaxies. The Milky Way and its satellites are part of the local group. The local group is falling toward Virgo. Virgo is part of Laniakea. Your address keeps expanding, layer after layer, each one containing the one before. And yet, here you are, in this specific place, in this specific moment, part of all those larger structures, but also right here, right now, breathing slowly, settling into sleep. The Magellanic Clouds shine in southern skies tonight, visible to anyone who cares to look, two small companion galaxies orbiting our own. The Sagittarius dwarf continues its death spiral, shedding stars with each pass through our disk. The Virgo overdensity hangs in the halo, a ghost of a galaxy consumed billions of years ago. And over 50 smaller satellites circle through the darkness, most too faint to see, but they're real, part of the Milky Way system, part of our galactic family. We are not alone. We never were. We exist in relationship, in context, in connection. The satellites remind us of that. They're our companions, our family, our context. Some will survive. Some will be consumed. But all of them are part of our story. Everything changes. Nothing lasts forever. Not stars, not planets, not galaxies. Even the Milky Way, ancient and vast as it is, has a future, an ending, a transformation waiting billions of years from now. Let's look forward. Let's see what's coming. Not tomorrow or next year, but in the deep future, when everything familiar will have changed, when the galaxy itself will be unrecognizable. Right now, at this very moment, the Milky Way is moving through space. Not just orbiting within the local group, but actually moving toward something. Racing toward it, actually, though on cosmic timescales the race is very slow. We're heading toward the Andromeda Galaxy. Andromeda, also called M31, is our nearest large galactic neighbor. It's a spiral galaxy like ours, perhaps slightly larger, containing maybe 1 trillion stars compared to our few hundred billion. On a clear, dark night, you can see it with your naked eyes, a small fuzzy oval in the constellation Andromeda, the most distant object visible without a telescope. That fuzzy oval is 2.5 million light-years away. The light you see left Andromeda 2.5 million years ago, when the earliest human ancestors were just beginning to walk upright on the plains of Africa. And that galaxy is coming toward us. We're coming toward it. The distance between us shrinks by about 110 kilometers every second. About 70 miles per second. Nearly 250,000 miles per hour. At that speed, you could circle the Earth in just over 6 minutes. You could reach the Moon in less than an hour. You could cross the entire solar system, from the Sun to beyond Pluto, in about 2 weeks. But crossing 2.5 million light-years, that takes longer. Much longer. In about 4.5 billion years, the Milky Way and Andromeda will collide. Let that number settle gently in your mind. 4.5 billion years. almost exactly as long as Earth has existed. As long as the sun has been shining. The entire history of our planet, from its formation to now, will happen again before this collision occurs. 4.5 billion years from now, Earth might not exist anymore. The sun will be nearing the end of its main sequence life, swelling toward its red giant phase. Humanity, if it still exists in any form, will be unrecognizably different, evolved beyond anything we can imagine. Everything you know, everything you've ever known, will be long, long gone. But the galaxies will meet. When people hear galactic collision, they often imagine catastrophe. Stars smashing into each other, explosions, destruction. But that's not what happens. Space is mostly empty. Even within galaxies, even where stars are densest, there's so much empty space between individual stars that collisions are extraordinarily rare. When two galaxies merge, their stars pass by each other like ghosts passing through ghosts. The probability of our sun directly colliding with another star during the merger is essentially zero. The distances are too vast. Space is too empty. But that doesn't mean nothing happens. Gravitational interactions will be tremendous. As the two galaxies approach, their mutual gravity will distort their shapes. The neat spiral structures will warp, stretch, become chaotic. Long tidal tails of stars will be flung out into intergalactic space. The galactic disks will tilt, twist, eventually shatter. The galaxies will pass through each other. Then gravity will pull them back together. They'll collide again, and again, each pass more chaotic than the last, until finally, after perhaps 1 billion years of this cosmic dance, they'll settle into a single merged galaxy. What emerges won't be a spiral anymore. The merger will destroy the disk structures, scatter the ordered orbits, mix everything together. The result will be an elliptical galaxy, a football-shaped swarm of stars with no particular structure, no spiral arms, no organized rotation. Astronomers have nicknamed this future galaxy Milky Way, a portmanteau of Milky Way and Andromeda. Not very poetic, perhaps, but descriptive. It will be the child of both parents, containing the stars of both galaxies, about 1.5 trillion stars total, one of the largest galaxies in the local group. During the merger, gas clouds from both galaxies will collide. Unlike stars, gas clouds do interact. They'll slam into each other, compress, shock, heat up, and compressed gas forms stars. The merger will trigger a spectacular burst of star formation. Millions of new stars will ignite across the merged galaxy, hot, blue, massive. The combined galaxy will blaze brightly, lit up by this generation of newborns, a starburst galaxy, one of the most luminous types of galaxies in the universe. If any conscious beings exist in either galaxy at that time, they'll witness spectacular skies. Bright young stars everywhere. Possibly nearby supernovae, as the massive stars complete their brief lives and explode. The sky might never be truly dark, filled with the light of countless suns. But eventually, the starburst will fade. The gas will be exhausted. Star formation will slow, then stop. And Milky Way will settle into its new form, an aging elliptical galaxy, gradually using up its remaining gas, forming fewer and fewer new stars, slowly fading as its stellar population ages. The supermassive black holes at the centers of both galaxies, Sagittarius A** and Andromeda's central black hole, will eventually merge. They'll spiral inward, emitting gravitational waves, ultimately combining into a single, larger black hole at the center of Milky Way. That merger will be one of the most energetic events in the universe, releasing more energy in gravitational waves than the sun will emit in its entire lifetime. But it will happen so far in the future, in such a different galaxy, that it's hard to imagine what it will mean to anything or anyone who might exist then. What about Earth? What about the solar system? Honestly, it's hard to say. The sun will likely survive the merger, simply because star collisions are so rare. But the Sun's orbit will change dramatically. We might be flung to the outer regions of the new galaxy, far from the center, into the sparse halo. Or we might end up near the core, in the dense central regions. Either way, our night sky will look completely different. The familiar constellations will be gone, scattered by the gravitational chaos of the merger. New stars will dominate the sky, some perhaps frighteningly close, their light bright enough to read by at night. But realistically, Earth probably won't exist by then, at least not in any habitable form. The Sun will be entering its red giant phase around the same time as the merger. It will swell, heat up, possibly engulf Earth entirely. Even if Earth survives physically, its oceans will boil away, its atmosphere will be stripped, its surface will be sterilized. The merger of Milky Way and Andromeda will be spectacular, but humanity, if it still exists, will be watching from somewhere else. Perhaps another star system. Perhaps another galaxy entirely. Perhaps as being so different from us that calling them human would be meaningless. 4.5 billion years is a long time. Long enough for anything to change. Long enough for everything to end and begin again countless times. After Milky forms, it won't be alone for long. The local group's other galaxies, the Triangulum Galaxy and the various dwarf galaxies, will also merge over time. Eventually, perhaps 10 billion years from now, all the local group galaxies will have combined into a single giant elliptical galaxy. And then, the universe continues expanding. Galaxy clusters and superclusters gradually fly apart from each other, carried by the expansion of space itself. The merged local group galaxy will find itself increasingly isolated, surrounded by ever-increasing distances to the next nearest galaxies. Eventually, trillions of years from now, the expansion will have carried other galaxies so far away that they'll redshift beyond detectability. Future astronomers in the distant future local group remnant will look up and see almost nothing, just their own galaxy and vast darkness beyond. They won't know that other galaxies exist. They won't know about the Big Bang, because the cosmic microwave background will have redshifted into undetectability. They'll think the universe is just their galaxy, surrounded by infinite empty space. All the knowledge we've gained, all the discoveries about the cosmic past, will be impossible for them to rediscover. The evidence will have literally flown away, beyond the cosmic horizon, beyond any possibility of observation. In a sense, we live in a special time. Late enough that we can see the afterglow of the Big Bang. Early enough that we can still see other galaxies, still measure the expansion of the universe, still piece together cosmic history. Billions of years from now, that won't be possible. The universe will have erased its own history. But that's so far in the future, so unimaginably distant, that it feels almost abstract. It's hard to connect emotionally to timescales of trillions of years. 4.5 billion years, though. The Andromeda collision. That feels more real, somehow. Still unimaginably far in the future, but concrete. We can calculate it. We can simulate it. We can almost picture it. The Milky Way, the galaxy whose structure we've been exploring tonight, will end. It will merge with Andromeda. It will become something new, something different, something unrecognizable. Everything ends. Everything transforms. But here's the thing. The stars won't die in the merger. They'll continue shining. The matter won't be destroyed. It will continue existing. The story won't end. It will just enter a new chapter. Milky will be different from the Milky Way, yes. But it will still be a galaxy. It will still contain stars and planets and perhaps life. It will still be part of the universe's ongoing story. Endings are also beginnings. The death of the Milky Way is the birth of Milky. The destruction of the spiral structure enables the starburst, the creation of millions of new suns. Nothing is truly lost. Everything is transformed. And you, lying here tonight, are part of a galaxy racing toward its destiny, moving at 110 kilometers per second toward a collision that will happen long after you're gone, long after everything you've known is gone, but moving nonetheless. The future is written in motion. The Milky Way and Andromeda are already on their collision course. Nothing will stop it. Nothing can stop it. It's inevitable, determined by the gravity and momentum established billions of years ago. But it's also billions of years away. For you, for humanity, for Earth, the Milky Way is stable, unchanging, reliable. The merger is so far in the future that it might as well be forever. Tonight, the galaxy is calm. The stars shine steadily. The spiral arms turn in their ancient pattern. Everything is as it has been for billions of years. And you can rest in that stability, in that calm, knowing that yes, everything changes eventually, but not tonight. Not tomorrow. Not for billions of years. The future will come. But right now, there is only the present. Only this moment. Only you, breathing slowly, settling into sleep. The Milky Way races toward Andromeda. But the collision is 4.5 billion years away. An eternity. Longer than you can imagine. Longer than you need to worry about. For now, for tonight, the galaxy is exactly as it should be. Stable. Beautiful. Home. For most of human history, we couldn't see our own galaxy. Not really. We could see the stars above us, certainly. We could see that milky band stretching across the night sky. But we couldn't see the shape, the structure, the true nature of what we were part of. It's like trying to understand the layout of a city when you're standing on a single street corner, unable to move, unable to gain any perspective. You can see buildings nearby, but the overall pattern, the design, the way everything connects, that remains hidden. Only in the last century or so have we developed tools powerful enough to see the Milky Way as it truly is, to map it from the inside, to understand its shape despite being embedded within it. Let's talk about how we see, how we've learned to see, how technology has given us eyes that can perceive what human eyes alone never could. The biggest problem with observing our own galaxy is dust. The Milky Way's disk is filled with it. Tiny grains, each smaller than a particle of smoke, scattered throughout the interstellar medium. Individually, they're insignificant. But cumulatively, across thousands of light-years, they block almost all visible light. When you look toward the galactic center, you're looking through the densest part of the disk, through the most dust. Visible light from the core, from the central regions where billions of stars shine densely packed, is almost completely absorbed before it reaches us. It's like trying to see through fog. Thick, cosmic fog that stretches for thousands of light-years. We can see the nearby stars easily enough. But the farther we look through the disk, the more the dust obscures. For decades, astronomers struggled with this. They could map the nearby regions of the galaxy, but the core remained mysterious, hidden, fundamentally invisible to optical telescopes. Then came infrared astronomy. Infrared light has longer wavelengths than visible light. And longer wavelengths can pass through dust more easily. It's like how fog might block your vision but doesn't stop radio waves or cell phone signals. Different wavelengths interact with matter differently. Infrared telescopes, both on the ground and in space, can see through the dust. They can peer into the galactic core, observe star-forming regions hidden within molecular clouds, map structures that visible light telescopes can never see. The Spitzer Space Telescope, launched in 2003, revealed the Milky Way's central bar in exquisite detail. Before Spitzer, we suspected the bar existed, but couldn't see it clearly. Infrared light made it obvious, undeniable, a prominent feature extending across the galactic center. Infrared observations also revealed the true extent of star formation in the galaxy. Many stellar nurseries are completely hidden by dust in visible light but glow brilliantly in infrared. We discovered we'd been missing huge amounts of star formation, entire regions of active stellar birth that were invisible to optical telescopes. The universe opened up. Suddenly we could see deeper, farther, more clearly. The dust that had frustrated generations of astronomers became transparent, at least to certain wavelengths. But mapping individual stars across the entire galaxy, that required something else. Something more ambitious. In 2013, the European Space Agency launched Gaia, a space telescope designed for one purpose: to measure the positions and motions of stars with unprecedented precision. Gaia has mapped over 1.8 billion stars. 1,800,000,000 individual stars. Each one measured, each position recorded, each motion tracked. It's the most detailed map of the Milky Way ever created. And it's revolutionized our understanding of galactic structure. Before Gaia, we had rough ideas about the spiral arms, about stellar populations, about how the galaxy was organized. After Gaia, we have precise data. We can see the spiral structure in the distribution of young stars. We can trace stellar streams from disrupted dwarf galaxies. We can measure how stars move, not just around the galaxy but also perpendicular to the disk, those vertical oscillations we talked about earlier. Gaia measures parallax, the apparent shift in a star's position as Earth orbits the Sun. By measuring this shift with extreme precision, Gaia can calculate exact distances to stars throughout the galaxy. It also measures proper motion, the tiny drift of stars across the sky over time. These measurements reveal how stars are moving through space, which tells us about their orbits, about the galaxy's gravitational structure, about its history. 1.8 billion stars. Each one a data point. Each one contributing to our understanding of the whole. And Gaia is still observing, still gathering data. The final catalogue, when Gaia's mission ends, might contain information on 2 billion stars or more. A census of the galaxy, the most comprehensive ever attempted. What Gaia does for stellar positions, other telescopes do for different phenomena. The James Webb Space Telescope, launched in 2021, is the most powerful infrared telescope ever built. It can see farther into dusty regions than any previous instrument. It can observe the earliest galaxies in the universe, but it can also study objects much closer to home, within the Milky Way. Webb has imaged massive stellar jets, the powerful outflows from young stars as they form. These jets, shooting out from stellar nurseries at hundreds of kilometers per second, help regulate star formation, prevent clouds from collapsing too quickly, shape the structure of molecular clouds. In visible light, these jets are often invisible, hidden by dust. In Webb's infrared vision, they glow brilliantly, revealing intricate structures, shocks, knots, the complex physics of star birth made visible. Every new image from Webb teaches us something about how stars form, how planets develop, how the raw material of molecular clouds transforms into solar systems. And then there are radio telescopes. The Very Long Baseline Array, or VLBA, is a collection of 10 radio telescopes spread across North America, from Hawaii to the Virgin Islands. By combining observations from all 10 telescopes simultaneously, astronomers can achieve resolutions measured in microarcseconds. A microarcsecond is 1/1,000,000th of an arcsecond. An arcsecond is 1/3600th of a degree. It's an almost incomprehensibly small angle. From Earth, a microarcsecond is the angle subtended by a grain of sand on the Moon. With this precision, the VLBA can map the positions of radio sources within the Milky Way with extraordinary accuracy. It can track the motions of masers, natural cosmic lasers that emit in radio wavelengths, as they move through star-forming regions. By mapping these masers, astronomers can trace the spiral arms, measure distances across the galaxy, understand the structure in 3 dimensions. Radio astronomy also revealed pulsars, those rapidly spinning neutron stars we discussed earlier. Pulsars are invisible to optical telescopes but beacon brightly in radio waves, their rotation creating lighthouse-like beams that sweep across Earth with clockwork regularity. Different wavelengths, different tools, each one revealing something unique, something that can't be seen any other way. Visible light shows us the stars we can see with our eyes, the constellations, the familiar sky. Infrared pierces the dust, reveals hidden star-forming regions, maps the galactic center. Radio astronomy finds pulsars, maps spiral arms, observes cold molecular gas. X-ray telescopes reveal hot gas, supernova remnants, black holes feeding on companion stars. Gamma-ray telescopes detect the highest energy phenomena, magnetar outbursts, pulsars, that mysterious gamma-ray excess from the galactic center. Each wavelength is a different sense. Like having not just eyes but also ears, touch, smell, taste, all working together to perceive the full reality of something. The galaxy is too complex, too varied, to be understood through visible light alone. We need all these tools, all these perspectives, to see it as it truly is. And the tools keep improving. New telescopes, new detectors, new techniques. Each generation sees more clearly than the last, resolves finer details, probes deeper into the hidden structures. Gaia is currently on its mission, still mapping stars. Webb is still observing, still sending back breathtaking images. Radio arrays are still tracing spiral arms. X-ray observatories are still hunting for black holes. The work continues. Our understanding deepens. The map grows more detailed with every passing year. A century ago, we didn't even know other galaxies existed. We thought the Milky Way was the entire universe, and those spiral nebulae were just gas clouds within it. Then Edwin Hubble proved that spiral nebulae were actually distant galaxies, island universes, each containing billions of stars. 50 years ago, we didn't know about dark matter, didn't understand why rotation curves stayed flat, didn't know that most of the galaxy was invisible. 20 years ago, we didn't have Gaia's precise stellar maps, didn't have Webb's infrared vision, didn't have the computational power to simulate entire galaxy collisions. And today, we can map over a billion stars. We can see through dust to the galactic core. We can track stellar streams from disrupted dwarf galaxies. We can measure the wobbles and oscillations of stars as they orbit. We can watch star formation in real time, in regions we couldn't see at all a generation ago. Imagine what we'll know in another 20 years. Another 50. Another century. The tools will improve. The maps will grow more detailed. The mysteries will slowly yield to observation and analysis. But some mysteries will remain. Some questions might never be answered. Dark matter might stay dark, its nature forever beyond our ability to detect directly. The far side of the galaxy might remain difficult to map, always obscured by dust and distance. That's okay. Mystery is part of the beauty. Not everything needs to be known, understood, mapped down to the last detail. But the drive to see, to understand, to map and measure and know, that's fundamentally human. That's what makes us us. We look up, and we wonder, and we build tools to see more clearly. Infrared telescopes to pierce the dust. Space telescopes to map a billion stars. Radio arrays to trace spiral arms. Each tool an extension of our senses, each one letting us see a little farther, a little more clearly, a little deeper into the nature of our cosmic home. For all of human history, people have looked up at the night sky and wondered. Before telescopes, before science, before we knew what stars were or how far away they might be, we looked up and we saw patterns and we told stories. The Milky Way has been part of human consciousness for as long as humans have existed. That band of light stretching across the dark sky, visible from anywhere far from city lights, impossible to ignore on a clear night. And every culture saw something different in it. Ancient Greeks saw spilled milk. The goddess Hera was nursing the infant Hercules, and he bit down too hard. Milk sprayed across the heavens, creating the pale band we see. That's where we get the name Milky Way, the galaxy of milk. In Chinese mythology, it was the Silver River, a celestial waterway separating two lovers, allowing them to meet only once a year when a bridge of magpies formed across the gap. Aboriginal Australian cultures saw dark dust lanes rather than bright stars. Where we see light, they saw the spaces between. The dark rifts running through the Milky Way became the emu in the sky, a constellation made of darkness rather than light, visible in the patterns of dust obscuring the background stars. In Norse mythology, it was the path souls took to Valhalla, a bridge between the world of the living and the realm of the gods. African cultures often saw it as the backbone of the night, a structural support holding up the sky itself. Andean peoples in South America recognized both bright and dark constellations within the Milky Way, seeing animals and sacred beings in both the stars and the dark lanes between them. Every culture looked up and saw something that made sense within their worldview, their mythology, their understanding of how the universe worked. They were all right, in a way. Not scientifically accurate, but right in the sense that they recognized the Milky Way as something significant, something that connected Earth to the broader cosmos, something worthy of stories and reverence. For thousands of years, we told stories about the Milky Way without knowing what it actually was. Then came the telescope. Galileo, in 1610, pointed his crude instrument at that Milky Band and discovered it was made of stars. Countless stars, too faint and too close together for the naked eye to separate, but stars nonetheless. The stories began to change. Slowly, over centuries, mythology gave way to measurement. Wonder remained, but it transformed, became scientific wonder. The kind that asks not what does it mean, but how does it work? In the early 20th century, astronomers were still debating whether the Milky Way was the entire universe or just one galaxy among many. The Great Debate of 1920 centered on this question. Were spiral nebulae distant galaxies, or just gas clouds within our own? Edwin Hubble settled it in 1924. He observed Cepheid variable stars in the Andromeda Nebula, stars whose brightness pulsates with a regular period. The period of pulsation is related to the star's intrinsic luminosity. By measuring the period, you know how bright the star really is. By comparing that to how bright it appears, you can calculate its distance. Hubble's Cepheids proved that Andromeda was far too distant to be part of the Milky Way. It was a separate galaxy, a separate island universe, containing billions of stars, millions of light-years away. The universe suddenly became vastly larger. The Milky Way was no longer everything. It was just one galaxy among countless billions, scattered throughout an almost unimaginably vast cosmos. Hubble's work refined distance scales, gave us the tools to measure cosmic distances accurately. Cepheid variables became standard candles, objects of known brightness that let us calculate distances across intergalactic space. And within our own galaxy, other variable stars serve similar purposes. RR Lyrae stars are old, metal-poor variables found in globular clusters and the galactic halo. They pulsate with periods of less than a day, and like Cepheids, their periods relate to their luminosity. By mapping RR Lyrae stars throughout the galaxy, astronomers can build a three-dimensional picture of the Milky Way structure. Where are the globular clusters? How far away is the galactic center? What's the shape of the halo? These stars are tools. Not just objects to admire, but instruments for measurement, standard candles scattered throughout the galaxy, each one revealing its distance through its pulsation. We've gone from seeing the Milky Way as spilled milk or a silver river to using variable stars to map its three-dimensional structure with precision. From mythology to measurement. From stories to science. but the sense of wonder remains. Different, perhaps, expressed differently, but still there. When you understand that those stars are hundreds of thousands of light years away, that their light has been traveling for longer than humans have existed, that you're seeing them not as they are but as they were in the deep past, that's as wonderful as any myth. More wonderful, maybe, because it's true. There's one frustrating limitation to our view, though. One region where our observations are permanently blocked. The zone of avoidance. It's the region of sky near the galactic plane, particularly toward the galactic center, where dust is so thick that it blocks almost all light from beyond the Milky Way. About 20% of the extragalactic sky is hidden behind our own galaxy's disk. When astronomers survey the universe, mapping distant galaxies, measuring the large-scale structure of the cosmos, there's a wedge of sky they simply cannot see through. The zone of avoidance. A blind spot created by the dust in our own galaxy. It's frustrating. Imagine trying to map the continents of Earth but being unable to see 20% of the surface because it's permanently covered in clouds. You'd miss entire regions, fail to understand connections, have gaps in your knowledge that could never be filled through optical observation. Radio and infrared observations can pierce through some of the dust, revealing hints of what lies beyond. But even those wavelengths are affected. The zone remains partially opaque, partially unknowable. We're stuck with this limitation. We can't move to get a better view. We're embedded in the galaxy, and the galaxy's dust blocks part of our view of the universe beyond. It's a reminder that even with all our tools, all our technology, we still have constraints. Our perspective is still limited by our position. But that makes what we have learned even more impressive. Despite the dust, despite being stuck inside the galaxy we're trying to map, despite the zone of avoidance and the limitations of our position, we've figured out the structure of the Milky Way. We've mapped its spiral arms, located its center, measured its rotation, discovered its dark matter halo. We've done all this from inside, from a single vantage point, using clever techniques and centuries of careful observation. Ancient peoples looked up and saw animals, rivers, paths to the afterlife. They were trying to understand their place in the cosmos using the tools they had. Stories, myths, patterns that connected Earth to sky. We look up and see light years, parsecs, stellar populations, chemical abundances, rotation curves. We're trying to understand our place in the cosmos using the tools we have. Telescopes, spectroscopy, mathematics, computer simulations. Both approaches are attempts to answer the same fundamental question. Where are we? What is this place? How do we fit into the larger whole? The ancient stories and the modern measurements are all part of the same human impulse. The need to orient ourselves. To understand our context. To know our home. The answers have changed. The Milky Way is not spilled milk or a silver river. It's a barred spiral galaxy containing hundreds of billions of stars, surrounded by dark matter, orbiting through the local group, destined to merge with Andromeda in the distant future. But the question remains the same. And the wonder remains the same. Just expressed in different language, different frameworks, different stories. You are part of a long lineage of people who looked up and wondered. Aboriginal Australians seeing the emu in the sky. Chinese astronomers mapping the Silver River. Greek philosophers speculating about the nature of the celestial sphere. Galileo discovering it was made of stars. Hubble proving we're just one galaxy among billions. Gaia mapping over 1 billion stars with unprecedented precision. All of them, all of us, trying to understand this band of light across the sky. Trying to know our home. The cultural interpretations matter. They're part of the story. The dark constellations of Aboriginal Australians taught them about the structure they saw, even if they didn't know about dust obscuring starlight. The Chinese Silver River recognized that the Milky Way was something flowing, something dynamic, even if they didn't know about galactic rotation. The myths contained truths, even if not scientific ones. They recognized that the Milky Way was significant, was connected to our existence, was worthy of attention and reverence. And now we know more. We know what it actually is. And that knowledge doesn't diminish the wonder. If anything, it enhances it. You are made of atoms forged in the hearts of stars within this galaxy. You are the Milky Way's way of knowing itself. Your consciousness is the galaxy becoming self-aware. That's not mythology. That's fact. And it's as profound as any ancient story. Rest now. The ancient peoples looked up and wondered. You look up and wonder. The impulse is the same across thousands of years, across every culture that ever existed. We are creatures who look up, who ask questions, who seek to understand. The answers change. The tools improve. But the wonder persists. Sleep now, inheritor of ancient questions. You stand in a long lineage of stargazers, stretching back to the first humans who ever looked up and wondered about that band of light. The Ara Lyrae stars pulse on, helping us map the galaxy in 3 dimensions. The Cepheids shine, revealing distances across cosmic space. The zone of avoidance remains, a permanent blind spot, a reminder of our limitations. And we continue observing, measuring, wondering, trying to understand our home. You are part of that effort, part of that lineage, part of that eternal human question. Where are we? The Milky Way has been answering that question, slowly, across thousands of years of human observation. And tonight, you know more about it than any ancient astronomer could have dreamed. You know you're in a barred spiral galaxy. You know you're 27,000 light-years from the center. You know dark matter holds it all together. You know we're heading toward a merger with Andromeda billions of years from now. You know your place in the cosmos more precisely than any human who lived before the 20th century. And yet, the fundamental wonder is the same. We are here, in this place, in this galaxy, part of something vast and ancient and beautiful. We've traveled far tonight. From the galaxy's origins to its future, from its structure to its motion, from ancient myths to modern measurements. We've explored what we know. But now, let's rest with what we don't know. With the mysteries that remain. With the questions that keep astronomers awake at night, wondering, calculating, searching for answers that remain just out of reach. Because for all we've learned, the Milky Way still holds secrets. Still surprises us. Still defies our attempts to fully understand it. Let's settle into the mystery. Let the unanswered questions wash over you like a gentle wave. Fast radio bursts. Brief flashes of radio waves, lasting just milliseconds, containing as much energy as the sun emits in days or weeks, compressed into the blink of an eye. For years, we didn't know what caused them. They appeared randomly across the sky, from different directions, unpredictable and bizarre. Theories ranged from neutron star collisions to alien transmissions, from evaporating black holes to phenomena we hadn't even imagined yet. Now we think most of them come from magnetars. Those neutron stars with impossibly strong magnetic fields. When their magnetic field lines snap and reconfigure during a starquake, they can produce these intense radio pulses, beaming energy across the galaxy and beyond. We found one in 2020. A magnetar within our own galaxy produced a fast radio burst, and we detected it. Multiple telescopes caught it simultaneously. The first confirmed galactic fast radio burst. It proved the magnetar connection. Solved part of the mystery. But questions remain. Not all fast radio bursts behave the same way. Some repeat. Others appear once and never again. Some have accompanying X-ray bursts. Others don't. Are they all caused by magnetars? Or are there multiple mechanisms producing similar signals? The universe rarely offers simple answers. Every solution reveals new complexities, new questions, new mysteries waiting to be explored. High above the galactic disk, cosmic rays stream through space. Not rays exactly, but particles. Mostly protons, moving at nearly the speed of light, carrying tremendous energy. They come from supernovae, from pulsars, from the most violent events in the galaxy. And as they travel, they affect everything they encounter. When cosmic rays slam into molecular clouds, they ionize the gas, strip electrons from atoms, change the chemistry. They help determine what molecules can form, how quickly clouds collapse, how efficiently stars are born. Without cosmic rays, the chemistry of the interstellar medium would be completely different. Star formation would proceed differently. The galaxy's evolution would have taken another path. We know cosmic rays matter. We know they shape the chemistry of space. But we're still working out the details. How exactly do they regulate star formation? How does their energy couple to the gas? What's the feedback loop between star formation and cosmic ray production? The calculations are complex. The interactions are subtle. The answers are still emerging. Threaded through everything, invisible but essential, are magnetic fields. The galaxy has a magnetic field. Not a simple dipole like Earth's, but a complex, tangled structure that follows the spiral arms, loops through the halo, connects the disk to the outer regions in ways we're still mapping. These fields regulate how particles move. Cosmic rays spiral along magnetic field lines, trapped, channeled, confined. Gas clouds collapse along field lines, forming elongated structures, filaments, the cosmic web made visible in star-forming regions. The fields also launch jets from young stars, from black holes, from anywhere matter is falling inward and needs somewhere else to go. Magnetic fields provide the structure, the channels, the highways along which energy and matter flow. But magnetic fields are difficult to observe. We can't see them directly. We have to infer them from their effects. From the polarization of starlight. From the emission of charged particles. From the shapes of gas clouds. Mapping the galaxy's magnetic field is painstaking work. We have rough outlines now, a general sense of the structure. But the details remain fuzzy, uncertain, still being refined. And then there's the Oort cloud. Far beyond the planets, beyond even the Kuiper belt where Pluto orbits, lies a vast spherical shell of icy objects. Comets, billions of them, perhaps trillions, spread across a region extending halfway to the nearest stars. This is the Oort cloud, the outermost boundary of the solar system, the edge of the sun's gravitational dominance. It reaches out perhaps 50,000 to 100,000 astronomical units from the sun, nearly 1 light-year. A quarter of the distance to Proxima Centauri, our nearest stellar neighbor. Objects in the Oort cloud orbit so slowly, so distantly, that their orbital periods are measured in millions of years. They're barely bound to the sun, barely held by its gravity. A passing star can perturb them, send them falling inward on long elliptical orbits that bring them into the inner solar system as long-period comets. We've never directly observed the Oort cloud. It's too far, too faint. We infer its existence from the comets that fall from it, from the statistics of their orbits, from theoretical models of how the solar system formed. It marks the frontier, the edge of our sun's domain. Beyond it lies interstellar space, the vast emptiness between stars, where the sun's gravity no longer dominates, where other stars hold sway. The Oort cloud is a reminder that even our own solar system has unexplored regions, places we've never seen, structures we understand only through inference and calculation. And if our own backyard holds mysteries, imagine what secrets the broader galaxy still keeps. Because here's the truth, the Milky Way continues to defy simple models. Every time we think we understand something, new observations complicate the picture. The rotation curve isn't quite as flat as we thought. There are subtle wiggles, variations, features that don't fit simple dark matter models. The spiral arms aren't where the models predict they should be. There are extra spurs, gaps, irregularities that our simulations don't fully reproduce. The stellar populations are more complex than we expected. Stars with unusual chemical compositions. Objects that don't fit cleanly into the categories we've created. Things that shouldn't exist according to our models but do anyway. The galaxy is messier than our theories. More complicated. More interesting. And that's okay. That's good, actually. It means there's still work to do. Still discoveries waiting. Still surprises hidden in the data. Science progresses not when everything fits neatly, but when anomalies appear. When observations don't match predictions. When reality refuses to conform to our elegant theories. Those are the moments when we learn. When we're forced to revise our understanding, expand our models, consider possibilities we hadn't imagined. The Milky Way teaches us humility. Reminds us that nature is under no obligation to be simple. That the universe doesn't care about our neat categories and clean theories. It is what it is. Complex. Messy. Full of exceptions and surprises and things we don't understand yet. And that's beautiful. You've learned a lot tonight. 100 facts about the Milky Way, woven into stories, into images, into a tapestry of understanding. But here, at the end, remember this: we don't know everything. We haven't figured it all out. The galaxy still holds mysteries. Fast radio bursts from magnetars that we're only beginning to understand. Cosmic rays shaping chemistry in ways we're still calculating. Magnetic fields threading through everything, invisible architects of structure. The Oort cloud marking a frontier we've never directly observed. And a galaxy that refuses to fit perfectly into our models, that keeps surprising us, keeps teaching us that reality is more complex than our theories. The mystery remains. And that's not a failure. That's an invitation. An invitation to keep looking. Keep wondering. Keep asking questions. Keep pushing the boundaries of what we know. Every generation thinks they've nearly figured everything out. Every generation discovers they were wrong, that there's more complexity, more depth, more mystery than they imagined. And the next generation goes further still. You are part of that ongoing story. Part of humanity's attempt to understand the cosmos. You've wondered about the Milky Way. You've absorbed these facts, these stories, these images of home. And now, you know enough to appreciate the mystery. To sense how much remains unknown. And to feel wonder, not just at what we've discovered, but at what still waits quietly beyond our understanding. Rest now in that mystery. Let the unanswered questions be a comfort, not a frustration. There will always be more to know. And that's beautiful. It means the story never truly ends. The exploration continues. The wonder persists. And here we are, at the quiet edge of our journey. You've drifted through billions of years of cosmic history, crossed vast stretches of space, and returned gently to this moment of rest. Everything you are, everything you've ever been, has unfolded here, within this galaxy. You don't need to hold on to the details. Let them fade. The Milky Way continues its slow, silent motion, holding you, just as it always has. If you'd like to drift again some night, there will always be more to explore. For now, rest. The stars will still be shining when you wake.